also matters from a demographic.
One, two, hey, hey.
You are currently the only person in this conference.
All right. Good. We're getting levels here. We're getting levels online. I like that. Waiting for my caller. Check, check, check. Hello, hello. Hello, hello, hello. Source. Yes, check, check, check. Hey, 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 hey. All right, here he comes. Okay, Dylan, can you hear me? All right, why don't you talk for us?
Testing, 1, 2, 3.
All right, we getting that okay? Keep talking, Dylan.
Okay, I will keep talking. What's up, everybody? Here we are on my YouTube channel. We're about to hit 1 billion subscribers. We're gonna have a pizza party. I don't know what else to talk about.
That feel good for you?
Feels
All
good
right,
for
we're
me.
good,
No
Dylan.
echo.
Go ahead and until we hear from Tim, go ahead and log into Ulster. I'm headed over there.
Cool.
I'll hand this to the presenter or to the MC. Work.
So I think we can get started. So the first speaker is Jacob Kostel from the VU University of Amsterdam, and he'll be talking about how I started chasing speculative type confusion bugs in the kernel and ended up with real ones. Please go ahead.
Hello, everybody. So this is going to be the story I will talk about today. And as a small teaser, I will start with the meme that my co-author created. So all we wanted to do is make a patch for these small Spectre gadgets in the kernel. And in the end, we ended up with the LWN article that made the kernel upgrade from the C standard C89 to C11. So this is roughly what I'm going to be speaking about today. So we'll start with some Spectre background, followed by an interesting case study that we found with our tool, and how this was revealing even more real bugs in the list iterator. So first, some very simple background on speculative execution. So we have an array here with 128 bytes. So it's a string, and then we have some very stupid code to calculate how long the string is. So we execute that iteration. So we start with I equal 0, and we access message with the index 0. And on the right side, we're going to see the cache layout. So blue means uncached, and as soon as something turns yellow, it will be cached. So now we access the first byte of message. So the first 64-byte of message will be loaded into the cache, assuming that you have 64-byte cache lines. And then we know that it's not 0, so we can count up. So now we do the same. So now for I1, that information will be already in the cache. So we can already start computing and count up. We do the same for I2, I3, I4, I5, and so forth, until I63, which was still in the cache. And then we reach I64, and that information is not yet in the cache. So the CPU needs to wait until that information is retrieved from memory, which is slow. So the CPU wants to already compute ahead. So it doesn't know what the outcome of that branch is, so it's starting to predict what the outcome could be. And the first 64 cases, it was always true. So now the CPU will think probably it will be true one more time. So very basic. And as soon as that information becomes available in the cache, it can commit that into the pipeline. So now what if the CPU is wrong? Can we fool the branch predictor into thinking that something is true even though it's not? So we look at the very similar code example here. So now we have an array that is 129 bytes. So the last byte is in the next cache line. And if we now look at the case where we already computed the first 128 iterations, and now we reach the last byte of the loop, and it is not cached, so we have to predict against something. So the CPU will think, all right, we just do count one more time, because we did that 128 cases already. But as soon as that information becomes available in the cache, the CPU will figure out that the 129th byte is actually the null terminator, and it should break instead. So it will roll back and commit the break case instead. And that by itself is just a performance optimization. But we can see that there are certain gadgets that can make this a problem. So the very canonical Spectre V1 gadget basically shows that you can leak information through this using a side channel. So, and how it works is you basically have something like get user, you load something from user space in the kernel. So the user space has, or the attacker has full control over that, what you're loading. And then you store that into X and check that whatever is loaded from user space is smaller than size. So you do a bounce check to make sure that it's not anything crazy. And then on the right side here, we see some kernel memory. So we see the array 1, which has 5 bytes. So that's what you're allowed to access. And around it, you have kernel memory, like either on the heap or in the stack that you should not be accessing. So now we have that bounds check. Everything is great in normal execution, and you can only access something within that array. Now what if we look at speculative execution? We trick that branch into thinking that x is smaller than size, even though it's not. So we can access, in speculative execution, we can access the content of that block, even though it should not be executed. So we give it some value of x that is larger than the size of the array, and we have some secret byte that is located after the array, and we load that. So that in itself is not necessarily a problem, because everything will be rolled back and will not be committed into execution anyways. So we load that secret into y, but now we have a secret dependent access in array 2, and that means you can basically encode that information in a cache line. And through that, you can use the cache information to use a side channel to extract that information in user space. So obviously, we don't want that to happen in the kernel. So what do we do? Or what defenses are already deployed in the kernel? So first, we have an lfence operation on the copy from user. So whenever you copy something from user space, you have a check which does access OK. So if that access is not OK, you should return 0. But then again, this is just a branch. And if you're unlucky, it will be mispredicted, and it could execute some instructions with an invalid access. So you add an lfence that basically makes sure that there's no speculation beyond this point. But the more interesting and more pervasively used operation throughout the kernel it's called array index no spec, which basically makes sure that an index is safe even in speculative execution. So here we see the do system call x64. It's used on 64-bit Intel or ARM, AMD on every system call. And you supply it the system call number, and it should be smaller than the number of system calls. And then you do an indirect call in the system call table. So if you mispredict this branch, you could supply it a larger number, which would make you execute some other memory that you should not be executing. So to make sure that even speculatively this is safe, you use this macro, array index no spec, to make sure that UNR will, even speculatively, be never larger than number of system calls. So what does the documentation about this actually say? So the documentation for Spectre says, for Spectre variant 1, vulnerable kernel code as determined by code audit and scanning tools is annotated on a case-by-case basis to use the no-spec accessor macros for bounds clipping to avoid any usable disclosure gadget. So what this in the end means is you don't avoid speculative execution, but you don't want any disclosure of secret information through it. So you use those gadgets, or you use the array index no spec in cases that you found with manual or static analysis. And then it says, however, it may not cover all attack vectors for Spectre variant 1. So when we were reading this, we thought we can do better. So Brian Johannesmeyer, my co-author, and I started a dynamic analysis approach to find these gadgets in 2019. So for our solution, we're using something called dynamic taint analysis. But what is it? I will start with a very simple example in user space. So imagine you have a function, main, with some arguments that you supply to the program, and then you copy argv1 into another variable with string copy, and somewhere later in the program, so this could be in a completely other function, another file, or whatsoever, so it doesn't need to be like strictly here. This is just to illustrate a very simple example. You use that variable in an execve. So obviously, we don't want that to happen. You don't want the user to control what programs you execute under your domain. So how could we detect something like this using dynamic taint analysis? And we're doing that, in this case, I show it with the DFSAN, which stands for Data Flow Analyzer. sanitizer in the LLVM project. So it's a LLVM pass where you can basically apply taint to a certain memory location. So for example, here we apply the user taint to the memory location of argv1 and say that is user controllable. And then we use the framework to propagate the taint. So we propagate taint based on the memory that we tainted. So it will basically like trickle down through the program to everywhere where that memory location or that memory values are copied to. So we see here that the taint flows to argv1 here, and through the string copy, it will be also tainting prog. And now we have a user controllable tainted proc argument to execve here. So what we need to do now is basically we do a taint sync and define when do we want to check taint. And in this case, we could make a taint sync that checks, for example, is the first argument of execve user controllable and has that taint? And if so, we detect the violation and we error out the program and print a report. So you might be thinking compiler-based dynamic taint analysis in the kernel. I don't know that exists. So basically, we have ported dfsan to make kdfsan for our project. You can find it under our GitHub. So it's not fully fledged, but it worked for our use cases. So basically, how does our approach work? So we have some random system call handler with a system call argument x. And within, we want to detect this Spectre gadget that we've seen earlier already. So we start by fuzzing the system call interface. And for that, we use syscaller to generate all kind of input that might be dangerous or that might create some interesting gadgets. And next, we apply the attacker taint label to all the system call arguments to basically signal that user space has full control over those arguments. And then we propagate the taint throughout the program. So that this could be like 10 functions deep in the call stack. It doesn't need to be straight here. And then we reach a conditional branch and we start something called speculative emulation. So imagine that x would be larger than size here, and you would, in theory, you would just skip over the block. But what we're doing now is we take a checkpoint, and then we basically execute the flipped outcome of the branch as if that would be the normal case. So now we start executing the block within that condition, even though x is larger than size. And we taint x here again. And now we use something called memory error detectors to identify unsafe accesses. So basically what we use for this is KSAN to detect out-of-bounds accesses. And we check if there's a KSAN access with something that is tainted, which would mean that you also have control over how much you go out of bounds. Because if you just go like always one byte out of bounds, it doesn't give you anything. You want a controllable out of bounds access. So that's what we use the taint analysis for. And then we apply the taint label, the secret label to whatever is loaded by that access. And then when we get to the point where we have a secret dependent memory access, this information gets encoded in the cache, and our cache interference detector identifies such a gadget. And then finally, we basically revert all the speculative operations and restore back to the checkpoint. And then we can just continue until the next branch and repeat the whole process. So that's the approach that we implemented in our tool, Casper. And in the end, we obviously take the Linux kernel, and then we take our runtime libraries together with our LLVM passes, which do the dynamic taint analysis and the checkpointing and so on. And we build the Casper instrumented kernel, and we fuzz that kernel with syscaller to report gadgets at runtime. And then we aggregate those in a statistics and build a website to basically present the results to show you what is the taint that caused this, what is the syscaller reproducible program, and then you can hopefully reproduce it and fix those. So with that, we've discovered 1,379 previously unknown gadgets. But bear in mind that dynamic taint analysis is still fairly limited in how much control you have. So it doesn't tell you if, for example, of a 64-bit pointer, if you have full control over it at some point or not. So if you have some masking involved, it could mean that you only have control over certain bytes of the pointer and not all of it. So to detect full controllability, you would need to use something more sophisticated as dynamic taint analysis. So now let's look at a case study that we found through our tool that we believe is almost impossible to find with a static analysis. And for that, I will do some background on the list for each entry macro that probably most of you have used in the kernel. But we will look at the internals of it, so I will recap that very briefly. So in the end, it's more or less just a for loop where the initialization sets the position variable to the first entry of the loop, of the list, sorry. And then in the terminating condition, we check if that element is currently the head element. If so, we stop iterating. And otherwise, we do incrementing, and we set the pos to the next entry. And in the end, if we look at it, and this gray area here is our struct, and we have the embedded list information down here, and we have some member that we access within the loop called data here, and pos will always be pointing to the start of that struct. So let's look at some example where we have a list with a head element and two elements. And now we basically start iterating over that loop. So when we do list first entry, we set pos to the start of the first entry, of course. And then we basically, within that loop, we access the data member and load that information out. So now we do pos equals the next entry. So we set pos to the start of the second element, and we repeat the content of the branch of the loop again and access data. So now what happens next is pos will be set to the next entry again. So in this case, pos will be set to this out of bounds memory area with the offset of the embedded list struct, but there's no list, the entry around here. The head element is not contained within the same struct as the elements. So this will point to essentially bogus memory area. And now we reach the terminating condition where we check if the list entry is the head, and it is, so we stop executing. But what if we now mispredict that branch? We tell the CPU, we think you need to do one more iteration of the loop, even though it's not supposed to. So now within that loop, since we are the attacker, the program will think that pos will point to a valid entry of the struct, but there could be any memory around that. So it will execute the content of that loop again, and it will access the member data, which could be any secret if we're lucky, and then it will load out that secret into some internal CPU structures. In this case, we call it the load buffer. And then an attacker could use a side channel to leak it. And this is basically possible on every list for each entry iteration that you have in the kernel. And since you have them all over the place, it's quite easy to find some cases where this gets a problem. So finally, we implemented a proof of concept exploit for one instance of this gadget to show that it works. But this is just the beginning of the story. So essentially, this is an issue that cannot be solved with a simple array index no spec. You cannot do a bounds clipping on this terminating condition. So you cannot apply the mitigations that have been used by now. So how can we fix it? In this case, we have the macro again.
I mean, this list for each entry goes around the list, and it also accesses the entries so that it's more convenient for the body of the loop. But you can also just have a list for each, and then the body of the loop can also take the entry. So do you have the same problem in that case or not?
You would still have the same problem.
Okay, thank you.
Because you can still mispredict the outcome of the terminating condition, and then you would just do get the position variable within the loop straight afterwards. So in the sense, your speculative window might be smaller because you need to calculate the position element within the speculative execution rather than doing it before.
Okay, thank you.
But I mean, there are so many iterators that I've just used this one as an example, because if we do all of them, they're almost the same, and most of them share the same issue. So how can we fix this? In the end, what changed is the terminating condition. So we still check the condition to terminate the loop is the same. But now we add basically the second line here, where we make sure that when we reach that terminating condition, even in a speculatively safe manner, we set the position variable to null. So we will still do a speculative iteration of the loop, but now pos will be set to null, and you can hopefully not use it to leak any dangerous information. But this also means that the iterator variable will be invalidated at the end of the loop. So it will be set to null, and there are 450 plus locations that use the list iterator after the loop. And we found out painfully by just making the fix and noticed that the kernel was panicking all the time. So luckily, we were pointed out to Coccinelle script that basically finds all these cases where the list iterator is used after the loop, so we could analyze them. And it turns out by looking at that list, there are actually some that are actual bugs that we found through going through that list. And now we're going to look at some architectural bugs, so no speculation beyond this point. Consider this an Alphins operation. We just talk about architectural bugs from now on. So we start with this code snippet. So we have, again, list for each entry, and we have rec as the iterator variable. And then within the loop, we check if the member rec of that has the address of underscore rec. And if it does, we found the correct element, and we break out of the loop. And after the loop, we'll basically check if that address is not what we were looking for, error out. So that looks safe, right? We can just use that. Some people have the opinion this is safe, some people don't. I'm going to show you it's not necessarily. So if we look at that, we see that the iterator variable will be used after the loop. And based on what I showed you before, you can already get the hunch that this is not great. So does it still look safe? In the end, it depends, but probably not. So we go back to a case study where we have a list again with two elements and the list head. And up here, we have the same code that I've showed just now with the line highlighted that we're executing currently. So for the first iteration, rec will be pointing here, and we will access the member of rec here. And then we use that to compare it to underscore rec. And we didn't find the element that we're looking for, so we continue. So we do the same for the second element. And now if you remember, rec will be pointing again out of bounds here. So if you use it after the loop, then rec will be using something that is out of bounds again. Yeah.
I think actually it's fine. It's just addition because of the ampersand.
Sorry, say again.
I think that it's fine because it's just an addition. It's because of the ampersand.
Oh, yes. So in the example that I showed here, it depends on the layout. But if you would imagine that, for example, the list embedded struct would be before rec, then you could basically, if you're unlucky, then the information, the underscore rec could be located below that head element. So for example, if you would imagine that this member would be below the list head. Then, for example, after the empty list head, there could be an element that where underscore rec is. But we have seen cases where you don't have the ampersand, so it's even more clear. But in this case, if you assume that underscore rec could be an arbitrary pointer, it's already dangerous. But if you assume it's pointing to an actual element, it depends on the stack layout, or on the struct layout, sorry. But we have shown that depending on how the struct layout is, if, for example, the member that you're accessing after the loop of the loop here would be located after the list embedded struct, you can still make it work. So if you're unlucky and underscore rec will be whatever this is pointing to, you could make a trick into not taking this branch, even though you didn't actually find that element within your list.
Like in Portal. Would it have been maybe easier if you just, instead of head being not an element of, whatever is in the queue, to make it an element of whatever is in the queue? Like have it just be a zeroed out structure allocated?
Yes, but I don't think the kernel will be able to change that anymore. Because usually what happens, so here we have an empty list head. So you could imagine this being, for example, a global variable. So you could just pad the struct around it to make it safe. You would waste some memory, of course, but that should be fine. But what you have most of the time is that this list head will be embedded in another struct. So for example, if you have a certain struct and it will contain the list head pointing to a list of something else, which you have most of the time, you would enlarge all of those structs that contain that struct by that many bytes. And if you have that basically in both ways, you cannot do that, because then the one would be enlarged to fit the other one, but in the area that you enlarge, you would have a pointer again to the one you're pointing to, and then you would have to enlarge that one again. So we are calling this type confusion in C because internally in the list iterator, it's using container off to perform on the list head, which is not actually contained in the struct. So we call this a type confusion because this resembles basically an invalid downcast in object-oriented programming. So you, for example, if you have a struct and you have a master type and some subtypes, you would use container off to go to one of the subtypes. But if you don't do that incorrectly, if you do that incorrectly, it's a type confusion. So we raised these issues on the mailing list, and basically we got the response from Linus that the rule should be you never use the iterator outside of the loop. And the whole reason this bug can happen is that we didn't have C99 declare variables in loops. We should finally start using variable declarations in for loops. So first I'm going to show you what the correct way is to do the code that we have just seen. So now we have a separate variable that is basically just used for iterating, and we have one that points to the argument to the element that we want to find, and we set it to null, and then we iterate over the loop, and only if we find the correct element, we set rec to that element. And then after the loop, we can trivially check if rec was set or if it's still null. If it's set, we found the element. If it's null, we didn't. So in the end, this ended up with moving the kernel to a more modern version of C. So you can finally declare variables within the for loop itself. Now a bit about my experience and submitting some of these patches. It's been a lot of fun, but it's also very time intensive, especially if you're doing a PhD full time. And I got around like 80 of the patches merged so far. which still leaves around 300 locations that are a problem. And unfortunately, patching has to be done one by one because they don't follow a certain pattern. They're all quite unique in their own way. But also, it means without fixing all of them, you don't have a real benefit of C11 or C99, because as long as you don't fix them, you cannot move the iterator variable into the loop. So for me, these tree-wide change sets were a very tricky start to submitting patches to the Linux kernel in general, because the same bug will need very different fixes depending on the maintainer and the subsystem, as most of you probably know. In general, it was also very difficult to know how to split those into the pieces that you can submit. And different subsystems have different rules about it. How far do you split it, or do you keep it in one patch set, and so forth. So very big shout out to Mike Rappaport, who's been a massive help in answering all my stupid questions and helping me to get this into a stage that was actually submittable to the mailing list. So we were thinking there might be even more type confusions in the kernel. So maybe it's time to build a new scanner for this kind of issue. So we were thinking in general, any use of container off could potentially lead in a type confusion. You basically just give it a pointer and you tell it what type you're casting it to without actually ensuring that whatever you're feeding it is actually the correct one. All you do is basically an offset operation to subtract some bytes. And if you do that incorrectly, you will have some bugs. So detecting those are ongoing work. So if you have any ideas or pointers on what to look at, I'm happy to take them as questions or after the talk. So as a conclusion, we started building a speculative gadget scanner, ended up with some real type confusion bugs, which caused the kernel to move to a more modern version of C. And now we're looking into more type confusion issues that we found in the kernel. So we have some examples already, but we're still looking to enhance our script and find more.
Okay, thank you.
Thanks.
So I have an online question I can start out with. This is from Dmitry Vyukov. He asks, can you share a bit about how you do speculative execution and restore the snapshot?
Yeah, so I left that out because it was just too much for this presentation, but we basically do all of that compiler based. So basically when I say we take a snapshot, it means we take a copy of the stack frame of that function and all the registers, but obviously that is not enough. So basically when we start the speculative emulation, what we do is every time there's a memory write operation, we store what was in that location before in an undo log. And then when we reach the end of that speculative emulation, we roll back and play back all the memory that was modified within basically that window, so that the memory will be in the same spot as it was originally. And then we restore the registers and the stack frame. And then you should be good to go and have everything in the stage that you were before. Of course, there are some limitations. So for example, if you write something to a driver or you write something out to the network, it won't work. So also inline assembly is fairly limited because we cannot instrument that with LLVM. So we have certain spots where we cannot do speculative emulation in. But we showed that it works in almost the most of the kernel.
Okay, thank you. So Dmitry, thanks you as well. Are there more questions?
Oh yes, so two questions. One is when we do the emulation, how can we do if there are several nested branches in a row? And then the second one is how many instructions should we take a look when we do the emulation in the first branch prediction?
So the first question was about nested branches, right?
Right.
So basically for this one now, we only flip one branch and then we execute basically until we think it's the end of that window. And then we roll back and then we go to the next branch. But obviously CPUs are smart enough to do nested speculation. So if you would want to do it properly, if you reach the second branch within your speculative emulation, you would have to take a second snapshot, fork off again, and mispredict that branch again, roll back to that stage, and continue from there. But we showed that you can find enough gadgets with just mispredicting one branch. And the second question, I'm not sure if I heard it correctly, but it was about which structs to look at, or
how many instructions should we take a look? I mean,
for the speculative, or
yes.
So basically, in the end, the issue could be in any list for each entry. So basically, any struct that you're iterating over could be an issue with list for each entry. But then it depends also. We found one case where, for example, the head element was contained in another struct, and then the member that you're accessing within the speculative iteration of the loop is something that you have full control over. So you do a memory load with something that you can just set with procfs, and then you control the full pointer. You can load something arbitrary in, and you can leak that through a side channel. For a lot more information, it's probably best to look at the paper or just talk to me afterwards. But it always depends how much control you have around that head element, or if there's anything secret to leak.
More questions?
Hi there, my name is Nick. I work on keeping the kernel building with Clang so people can do more interesting research like this. So very exciting to see this. As soon as I saw DFSAN, I thought, ooh, I'm sure we can find some interesting bugs with it. So very exciting to see this line of research. In particular, one of the issues that we've dealt with significantly a lot in the past is information disclosures to user space, where some structure is filled in with kernel memory and generally pattern gets into user space. In your experience working with DFSAN, do you think DFSAN might be an appropriate tool for us to use to try to automate finding more instances of these information disclosures?
Yeah, I think so. I think there are a lot of applications that you could use the kernel DFSAN for. I think this is definitely one that might even be suited better, because you just taint some memory, and if that one flows to user space, you have a problem. For us, we were using it to determine controllability, which can be tricky. But yeah, thanks for making it possible to compile the kernel with LLVM. In the beginning of this project in 2019, there was no LTO support, so we were doing it with a GLLVM, which was like massive gigabytes of LLVM bitcode, and it was horrible. So when we moved to LTO and you were using our passes on that, it was making our life a lot easier.
Oh, Habit here is useful for more than one thing. Yeah, really cool. Thanks.
More questions? Okay, so thank you. Okay, so thank you everyone for coming. So our next talk will be from Arnaldo Cavallo de Mello, who will be talking about profiling data structures.
Hi, good morning. My name is Arnaldo. I work for Red Hat since, I guess, forever, for a long time. And we'll be talking about something that people have been asking me to do for a long time, which is trying to combine two tools that I work for a long time as well, which is the Linux perf tools that I maintain in the Linux kernel, and P-hole, which was a tool that I wrote a long time ago when I started looking at data structures in the Linux networking stack and how to reorganize them to make them smaller, more cache efficient, before I was even working with profiling and perf. So it's data structures. Normally, when you are profiling, you are looking at code, where you are, where things are happening, and not specifically on what things are being accessed. A data structure can be organized in many ways. If you do it badly, it will use more memory. The placement of all the fields have to be done in such a way that you exploit cache locality effects. You access a field, the next one you want will be afterwards, so you get just one cache operation bringing things from memory to the cache hierarchy. So it's important to think about it. Projects like the kernel have lots of work on having these in optimal placement, but this usually requires that you know a lot about the code that you are working on. So I was talking with Eric Dumazier that does this a lot yesterday, and said, "No, how do you do it? Use some tool." We say, "Yeah, I use P-hole to see the layout, and I use what I know about networking and what I know about how cache hierarchies work." So, but yeah, but we should try to automate that. And as we will see, there are facilities in hardware now that help us to do that. And there are tools in perf that are exploiting these to some degree. There are some problems. I will show what those problems are and what ideas are being I'm thinking about, or the people are thinking about, for the tool to do more and require less domain-specific knowledge. So it's if on a CPU you have a cache hierarchy. So the closer to the CPU you are, the data that you are going to access, the better. It will be faster. But you have this thing about the first level, second level, the last level cache, and then you have memory that are not local to your CPU. It's on another NUMA node. So you have to try to avoid accessing things in a non-optimal way. So just to recap, you have like the ls topo utility shows you on this machine, my machine, which is just a notebook, more or less the hierarchy. If it was a NUMA, you would have another block like this connected to this, and then there would be an interconnect. AMD has a kind of interconnect. Intel had QPI and now has Ultra, a new one since Skylake. The problems that we are thinking is like you have non-cache aligned arrays, and then when you access something, you get part of it in a cache line and the other part on another cache line. We are trying to avoid that you have things that are mostly read with things that are mostly written on the same cache line. If you have that, as we're going to see, the cache line will be not, it's effectively as nullifying the benefits of the cache. Lots of this was fixed over the years in projects like the Linux kernel by profiling and adding annotations to lots of places. So we should learn from it. So, but it's tedious. Lots of this was done, but manually tinkering. You think that this, like I said from Eric Thomas, you think that this is wrong because you see the cache line in your mind and etc. But let's see how to improve that. People just, I know what are the hardware limits for this, and we are not getting there. So let me try to find what are the issues, and then they do some perf stat on it, look at the counters, and then they do some changes, and then try it again, it improves it, and then try to find some explanation for that. Sometimes it's difficult. The guys from AMD were talking about some cases where they couldn't believe that the accesses on one CPU core would prime the cache for another CPU, and then the performance, they got to find the performance regression by just trying one thing after the other. And so they were asking if perf could try to help with that. We were discussing some ideas, perhaps in the future. So manually doing it. If you look at the kernel's commit log, Git repository, and look for false sharing, let's say, one of these issues, you're going to find lots of places where people sometimes use perf to find this already, using a tool that I'll be describing. And in other cases, they don't report what they use it, but they fix the issues nonetheless. The first example. So Eric in 2021, recent, there are two variables, one after the other. And one is for something, the other one is for something unrelated or mildly related. So the memory allocated and the number of sockets allocated. So they were one after the other. They were less than, they fit into a single cache line. So when you touch one, you invalidate the other. What he did was just added that cache line and line in SMP to both, so they are now at the start of a cache line, and you remove this problem. So that was the way he was doing it. We are thinking how to detect this, like, oh, this is a cache line that's being validated frequently. What is in there? Oh, two variables. Oh, maybe those two variables are not related. So the suggestion the tool would do, would be move them. You could even write a patch, let's say. Another case was looking at the kernel. The last line is the commit log message. He was always, when some decision, when there was this bitmap and then there was some condition, and on this condition he was unconditional, this condition was setting some bit that was related to some block or something like that. And so the solution that he did was to test if the value there was already the one that was desired. And if so, don't touch it. And so he got an improvement with that. So basically, it changed it. It was like sector dirty, set bit, no, test first and set afterwards, and got the performance improvement. A page counter. Two variables, one was mostly written, the other one was mostly read. He used perfc2c, which I will describe, and the facility in the processor that allows perfc2c to do the work. There is the bug report, and then the fix. The fix was moving it to another place and documenting this. So the first time we see PA hold on this presentation, so this is the new struct. So you see that PA hold shows the layout with the offsets, the size of the types, and the cache line boundaries. So parent is now on a different cache line than usage. So that specific problem was solved. So for the layout, when P-hole started, it was using dwarf. That's what GDB uses, etc. But it's really big. And then there came BPF, and BPF needed something more compact, just like Solaris had with CTF. So now, when you build the kernel, it gets the debugging information, the dwarf that GCC generates, uses P-hole, converts to BTF. BTF is linked with the kernel. It's always available. It's fast to access. You have it always there. So it's much more convenient now, and it's being used for lots of cases. And this tool is one case where it will be used again. It also records information about per CPU variable types. So you can use that as well to do some other analysis. There are patches now that are recording, proposing, I will talk about that later, but proposing recording the types for all global variables, not just per CPU. So it's compact, it's from BPF, it's used in BPF, for example, for compiler wants to run everywhere, to compare the types that are used on some BPF bytecode in the kernel, and then do adjustments, relocations if needed, so that you can use the same BPF bytecode for different kernels with if the kernel changes on the district that's used, you adapt. If you look at syskernel BTF is where it's there. You see the size for VM Linux. Then you have 204 entries there, one per module. The modules have just the types that are unique to this kernel module, and refers to the main VM Linux for the types that are there to avoid duplication. And so nowadays, if you go to command line and say p-hole whatever, any type in the kernel, it will instantaneously print the definition for this. And then you can see some interesting things like the cache line boundaries, if the last struct has padding, and this can be used for all kinds of analysis, interesting decisions. Inside the kernel, like the kernel can use this information to, like the BPF verify uses this to make decisions. So it's interesting to have this kind of detail. So you can think about like, oh, before that list head, there is, I will put a list head just after that 60 bytes whole, the alignment. So what's before it, it's not it's not something that is important, perhaps. The CPU helps, the new CPU. Intel, since a long time ago, they have PEBS, or precision enhanced branch sampling or something like that. And AMD has something similar, and ARM has as well. ARM uses like hardware tracing and then synthesizes the perf record events in user space, and then the rest of the tooling can consume it. First step, the example for PEBS describing what it does. Basically, you ask the processor to randomly sample load operations, and when it finds some load operation that is over, let's say 50 cycles, so that's taking too long, and then I want to sample this thing, I want to record what is the cache line where this happened, the data address for that's being accessed on the cache hierarchy, what is the IP address that caused this, and then you can, and what was the load latency, and then there's some information about weighting this sample. What we have in perf that to help with that? As I said before, perf stat can be used as a crude method. You can run it before, then you do a modification, run it again, you see the counters, and then you infer. You have perf main. That's the first one to use this load latency stuff. We're going to see some examples. C2C, cache to cache, that is perf main doing something else to try to match what is writing, what's reading with a high load latency. There are several articles about using it, people using it in the real world. On the perf wiki, that will be a link at the end, there are some pointers to these, so you can see, oh, how people use this, what was the use case, and then try to use this as education material. But we should improve on top of that. Perf main loads and stores, and the load latency was written by Stéphane Aranian, and several other people over the years have been helping in improving it, adding new features. So how does it work? If you do perf main record -A for system-wide, and then run it while that workload is running for 1 second, which is the usual way for you to run perf for a period of time, then you can see what are the memory accesses that were happening in the system during this 1 second. You can see the various levels of the cache hierarchy, and if it was a miss, and etc. And you can infer something from this. Using the usual perf workflow, if you remove that -A, then it's not system-wide. What will be profiled is just a sleep process. So it's just a few events that happens when you are running that specific workload. But you could replace that with perf main record -C, and then see what's happening on just a subset of the CPUs of the system, or a C group, or so on and so forth. So a familiar workload, I was doing a kernel build, and then I did perf main record for 1 minute. And then you get different from the other one. For this specific, for the whole system, you see that the data symbol is one of the things that we have to work. It's difficult to map back from a data symbol to a variable. I mean, so you don't have a map that says, so here is this lab, there, that's, I mean, there are something that you can map back. That strlen was on some kernel read-only memory. The other one, the data object, we resolve it, but not the data symbol. Perf C2C, cache to cache. It's trying to see the loads that are slow and match for the same, using the data cache line that's being accessed, match with the writes. And so you will look, who is invalidating this? And then you will try to resolve this by moving to different cache lines. One thing that the PEBS load latency can give you is the offset inside the cache line. We're going to see this later. So the origins for C2C were in HPUX. This guy, Dick Follis, was hired by Red Hat sometime to work on having something similar on Intel, since they realized that PEBS had provided the hardware mechanism that was available in the past and allowed this tool to be written in HPUX. So they come up with proof of concept. Then G.E. Osha got this reorganized so that it looked more like a perf subcommand. And then after so many iterations, we added it to perf. So the C2C output, instead, perf main was just showing the memories where there was latency, so the areas, but it was trying to match with the write operations. It will show lots of information about NUMA nodes, how many CPUs accessed that. There are lots of information. So that's one of the problems of the tool, is that because it's difficult for you to interpret the results. But let's try. So you run like this: perf C2C record -A is lib 1 system wide, and if you do perf evlist to see what was being recorded. So you're going to see that is the mem loads on the CPU performance monitoring units. And furthermore, it's configured to record just the load operations that took more than 30 cycles, 30 CPU cycles. You could say 150 and get more Newman node traversals, or you can put even more if you want to see something that's really contended to reduce the amount of data that's been collected. So it's a way for you to filter at the processor level. So it's a lot of information. I mean, just like with perfmem, it will say like that what was the kind of operation that caused this, but this is with perf script and looking just at the events on CPU 4 and for when it was idle. Even when idle, there are a lot of things happening. So what was really asked? You do perf evlist -v to see the details for this event. So on the sample type, you ask what is to be on each of the samples. You're going to have the IP, the TID, a timestamp, the address, but most of this is used for all the events. For this specific case, you are asking for the data source, the physical address, and the weight struct, so that you can like apply some weight based on some numbers that the hardware provides. And what's on the sample data SRC? You have the load latency that's obtained from PEBS or equivalent part of the CPU from other architectures like IBS on AMD. And you get the opcode if it was a load, a store, a prefetch, or an execution. You have the memory level that this data is being accessed, the TLB, Snoop, that there are lots of information on this. We are using basically part of this, but more can be done as we get this more tools using it, more people aware of what's possible. So the weight, it's hard to provide a number. How expensive this sample action represents. So the profiler uses this to scale samples. So the header, I'm using those comments because this is the usual workflow for perf. You run a record phase for some events, then it generates a perf data file, then you can use like perf report header only and see what's collected. So again, the sample type is like the show before, the number of CPUs, there is information about topology. There are lots of other information that are collected when you run this comment. When you say perf C2C report stats, there are key metrics there are way more metrics than these, but the one we are interested is this hit modified. Is when you get to the cache, it's there, but it's marked as modified. So you have to go to the other cache and get this information to synchronize with your cache. This is not a Newman machine, so only local hit modified happen. When you have, as we saw on that LS topo picture, you have caches that are local to each core, and then you have less level cache. So it could be invalidated one of the CPUs, and the other CPU is accessing, so it has to go there and synchronize. That's what we want to see. So the first shared data cache line table, it will show what are the cache line addresses that are being contended the most. It's there are way more information about the remote hit temps, but I compressed this to fit on the screen and to show just the local hit temps. So we see this and we pick one of those and start analyzing. So we get one of those is this one. So the tool will tell you the number of hit modified that code address is finding. And we'll try to resolve the code address to a source code line. So at the end, you have it's on the mod node page state on the VM stat file and line 379. and then the other ones as well. And so you see that some are load operations. Next step, so we have to look at the offset. You see that CL offset is the offset inside this data cache line where the access caused where the load was done. The field on one of the cache lines, on one of the data structures that we're trying to find out which one is. So we look at it, we see that 3 fields being accessed because there are 3 different offsets, or perhaps one is an array. And we have to find out what is the data structure. We have to look at the source code. So if we go to VM-stat379 using another perf tool, which is perfprobe, perfprobe will locate the dwarf debug information that's appropriate for this kernel. And if you use capital L and VM-stat.379, then you show the source code for that. So at the line 379, we see that it's a struct per CPU, PG-dat. So PG-dat, we have to find out what is the type for that variable. So if we use another tool that's with p-hole, which is pfunct, and you tell the name of the function, it will use the BTF information that's always available, and we'll figure out this, and we'll show that PG-dat is struct PG-list data. And then we look at PG-list data and look for that field that per CPU node stats, ask for something before and after, so we discovered it's this cache line at the end of that function. So now we have offsets in there and sizes for the function, for the fields, and we can figure out what are the fields. So this is manual. We want to have this automated, or move, at least helping move when navigating the profile. You click there and it opens the annotation view, and then you can click on the type, a p-hole browser would appear, and then you would move more quickly. So lots of manual steps. We have to streamline it. We have a perf-annotate browser, a TUI. So yeah, and we should go to the p-hole automatically back and forth. So if we go to refresh CPU VM stats, we're gonna see who is writing.
Here, Arnaldo.
Yes, Peter Zilka would like to join you. Go ahead.
So the compiler already knows what data structure and which variable inside it is related to the instruction it emits. So when we have a code address for a load or for a store, the compiler knew what data structure is associated with it. We don't need to go reverse engineer that.
Yeah. Yeah, I'll get. I think I will get to that on the next slide. I mean, the compiler could help. That's something that Stefan Areni at Google said that he was working with the compiler guys at Google to try to.
Yeah, but he said the same when C2C was introduced. I almost nagged C2C for not doing this.
Yeah.
And it's still not done.
You're right. I mean, this is he was a guy who was complaining about the C2C. So this presentation is about me finding time to do the presentation, to get to the issues, to get to the complaints, and try to work on this. So I have most of this in my cache now. So I hope in the next weeks or months I will be getting to what you were alluding to.
Okay, but yeah, the tools people should get involved because it's
yes.
to reverse engineer this data when the compiler already knows it when it writes the instructions.
Right. I agree.
You want a box? Here.
I mean, on risk architectures, yes. On x86, you have one instruction that access multiple memory locations. So you still need to eventually figure out which one of these you're actually accessing. The
Those
compiler could
instructions are
help.
fairly rare. Yes, they do exist, and there is, but for most cases, it's just a single memory location, and those cases are trivial to do. The other instructions, yes, they're a pain. But let's just do the simple things first.
Messing with compilers is not something I would call simple, but okay.
Yeah, I mean, Joe Mario at Red Hat, he uses these and fixes problems. It's cumbersome, but it gets us to where we were not before. So it gets us closer to where we want. And again, this presentation and trying to get more people. There's something else. The AMD guys had a problem, and after they fixed it, they realized that, oh, if I had perfC2C, I could have saved the time at diagnosing this. And they realized that perfC2C doesn't work on AMD, so they submitted the patches to make it perfC2C or low latency, etc., work on AMD. And the ARM64 guys did the same. So there are more people now looking at this and hopefully understanding the code, the issues, and hopefully you're going to get to the next step. I was not even like too much worried about not having solved this so far, because then Plumbers is for that, just to raise the question, raise the problems, and try to get more people involved. So we do this reverse engineering and find out where was that it causing the invalidation right into that cache line. And if you look at the comment for this specific data structure, people realized it and did it in such a way to avoid going to other NUMA nodes. But there is still the problem on the current CPU. So this problem may be intrinsic to this specific algorithm. I'm not going into that. I'm not analyzing this to the end. I'm just showing this specific case because it was the one that appeared and that I could use as an example of the difficulties involved with the current solution. So to incrementally help with this, like increment people who are using it already, on the peer hole, we should have, let's say, another option to ask for offsets inside cache lines. So you had the offset from the start of the struct, but we want the offset from the start of the cache line. Yeah, like PG that in the previous example was on the last cache line, and then we had to do some calculations to get to those offsets. Yeah, so it's all focused on when things happen, not on the data, but you have to look, but it helps to figure out to some degree. How we can get back from symbols, the compiler helping us is not one that is there, but it should be. But because as a tooler, I'm mostly trying at first to use what's available. I'm not going to change the kernel or change the compiler. I would love to do this, but this takes more time. So using what's there can improve the current situation and show what are the shortcomings with the compiler, with the kernel, with how we build things, and etc. And this is like a detour. Like with perf C2C, you have the usual perf workflow. You have to record, get the perf data file, and then do post-processing analysis. This is okay in many cases, but in other cases, it's really cumbersome because you have lots of data. So we have to use BPF to solve one more problem. So we have now in perf several BPF scales. So perf now uses BPF to do in-kernel aggregation, to create like virtual counters, or to do things like BCC does. using LibBPF. So you have several features like off CPU profiling, locking contention, statistics about kernel work, like for how long it takes from kernel work to be scheduled and then run, and all sorts of things can be done along with perf. But behind the scenes is BPF with perf, so they are combined while preserving the perf workflow. So the way you specify what you want to profile or trace is the same, but behind the scenes it uses BPF. So perf lock contention, capital B, to use BPF, it works just like you do that, and after a while press Ctrl+C and it provides information about what it aggregated in kernel. So we are now considering using adding sampling to BPF, so that when sampling the interrupt happens, a BPF program can run and then do some filtering and in the kernel or do aggregation. So perf C2C could be done this way, doing aggregation there, and then when you stop, you get BTF already talked. Code annotation, we have perf notate and things like that. This is a slide about the effects of hardware problem mitigation. But I don't have time to show that. But this is just to exemplify how code annotation is done. You have the percentages for the events that are being, and then the idea, the end result that we want is to do data structure annotation using PA-hole. Instead of centering on the code, center it on the data structure. So we're gonna get that information and show in the data structure what are the things that are being contended, and perhaps help give hints about changes for you to do, or do it automatically and recompile the kernel. That would be the end result. Yeah, and here you have lots of links for more in-depth texts about cache coherency, what's involved, what we are trying to avoid. And then there is the article for Joe Mario, the original one for perf C2C, and these useful links on the perf wiki have all this and more. So that's what I had to say today. Are there any more questions?
Okay, so to start out with this online question, this is from Igor Guryanov. Perf seems to generate a lot of information. How badly does it distort caching statistics, especially on systems with small caches or multi-core systems? Would the data still be usable?
Can you repeat?
Yeah, the problem is it generates lots of information, so he's concerned that it's going to, perf itself will be corrupting the cache.
Yeah, I didn't got it. But it's about statistics about the cache validation, or
It just says, how badly does it distort caching statistics?
Depends on how much data you generate. So if you have a long-running stable process, you can sample at a very low rate, and that will generate less data per time and disturb caches less. It's always a trade-off. I mean, watching something changes that thing you're watching. It's always.
Yeah, I think it was. Yeah.
But overall, perf is extremely overall perf is extremely useful in production. So like, you can sample and not distort like beyond what you're sampling, and then you're done with it, and you don't really need to care about it. So in general, like you might see like small spikes and latencies or the effects of destroying the cache, but in general, that's not something I'd be concerned with.
Yeah, but this is, I mean, this is very specialized stuff. I mean, for the use case I see is the AMD doing a patch to improve scheduling performance on their chip, and then there is a small change in layout for per CPU variables, and the performance goes down, and they can't figure it out. So using a tool like this will help that. The previous question was about, I think that it was about the high volume. Yes, as Peter said, you can reduce the frequency, or you can even ask the PEBS to only record things that are over that the number of cycles. So you can use this in production. And if we use something like the BPF mode that is being thought about, you can avoid having a big file. So it's another way of reducing the overhead of doing this kind of analysis.
Hey, Arnaldo, I've got a question on Nick. So I guess maybe an interesting observation and then a perhaps naive question. The statement is if developers are interested in trying to find when they have excessive padding in their data structures. I saw an interesting zero-day report the other day. So it looks like the folks running zero-day bot, they're starting to run Clang Tidy, and there's an analysis in there called excessive padding warning, and it will print if you have like more than 10 bytes of padding or something. I don't know precisely what the heuristic is, and it will actually tell you the optimal sort for your members. So I think PA hole is fantastic. I love it, especially once you start embedding structs within structs.
Yeah.
You very quickly, like you kind of.
Yeah, you can expand them.
Like
and
you without jumping to the definition, you can't do the alignment in your head of like, what is the excessive padding kind of thing.
What does Clang Tidy think is optimal?
I don't know. It'll do the sort and it'll tell you how to minimize the padding.
Yeah,
right?
minimize, but that might not be optimal.
Sure, but it's going to ignore like, huh? Sure. Sure. Right, but you need some kind of attribute or some pragma or something to say like, I'm doing something tricky here, so ignore this from the analysis. Sure, those exist. Anyways, the perhaps naive question about some of the cache line sharing stuff is, so I'm almost curious, like cache lines are different, I assume are different size between different machines, different architectures, different microarchitectures. Is there ever the case where someone is maybe over-optimizing for a specific machine with some of this cache line sharing stuff, where maybe things now are separate cache lines?
No, I mean, in the kernel, when you have those annotation, the cache line aligned on SMP, it takes into consideration the cache line size for that specific architecture. So the alignments in different architectures will be different. So, I mean, there are all sorts of, Eric Dumazet was saying something like, you have to disable cache line prefetching. So because it's 64 bytes, but if you have it enabled, and sometimes the machine comes enabled in the BIOS, so the cache line is not 64 bytes, it's 128. So the kernel should see that and behave in a different way. Or this, what he does is disables this. What PA hole could do is detect this and show. So this is the cache line size, but this is the prefetched cache line size, and then this can help in understanding performance problems. So there are more things that can be done in PA hole, and I'd love to hear it written, send me emails so that I can go on making it better.
Yeah, thanks.
I have a follow-up question for that. So you showed multiple ways to fix those fault sharing, right? Yeah. One was the cache line aligned, but the one was also just reordering the members.
Yeah, right.
And that one would not take into account like different sizes of cache lines, right? It could work on one, but not on the other. So is cache line aligned the best way to do it? Because
I mean, I was just trying to show some examples, and perhaps that was the quickest way for the guy to fix that at that time, and Eric Dumazet to do it. But if there is another way of getting it close to another variable that's read mostly, you group first the read mostly, and then you group things that are related, which is even better, because then you get something and then you get the other one for free. So that would be another way to do it, a better way to do it. You see? So that's another way. Instead of adding all this padding, you get the padding and put something that will be probably used after that one and will not generate false sharing.
Yeah, because if you have a struct with only 2 members and
Yeah.
they are false sharing and you align them, you
Yeah.
would make it super large. You would
Yeah.
need 2 cache lines for.
Yeah, right. You should reorganize your data structure, break it down. We use another algorithm. There are many ways to do this.
Okay, so we're almost out of time, but I sense, is there a question over? Go ahead, please. Do you have a question?
I was just going to mention that like if you just look at struct page, like it will assume 64 byte cache lines. So like it's kind of like hard coded into the notion of like how members are distributed in the data structure. So like in that sense, like I guess PA holes showing like reorder members instead of like
right. PA hole has a dash reorganize option, but it's really naive.
Right.
Really naive. Just moving to make it smaller. Having this kind of hints from hardware could get into this algorithm and then say, oh, those things are not causing, or combined with compiler help, combined with I mean the annotations that are already there. So you could there was somebody talking about the kernel doing data structure reorganizing for security reasons, and people are saying, oh, it's not a problem if you move just the cache lines around, because then all the annotation that were done remain valid and you get some randomization of the access. So I mean there are lots of things that can be done with something that's seemingly, I mean, silly, yeah, the order of fields in a data structure.
To pick up on a few comments before, unfortunately, it's not completely an exact science. Cache lines are not necessarily architected, which means even for a given ISA, you can have different implementation with different cache lines sizes. For PowerPC typically is like that, and we have 64 bytes or 128 bytes in some cases. Struct page is struct page. I mean, the point is, these things is, we don't want to make it twice as big. And so at the end of the day, we do the best we can for the most common case, which is 64 bytes. And it's going to be a lot of these, where thankfully 64 is the most common cases and probably where people will strive to optimize for. And then we see where we go from there.
Yeah, another comment that somebody made was sometimes you optimize the data structure, it improves some workload, but then pessimize another one. So you have to have that in mind.
Okay, so we're out of time. We have a final comment from Feng Tang, who is looking forward to the annotations. So thank you very much.
Okay, thank you for being here.
Well, let's get started with Jason's, just about get started with Jason's talk about the random number generator. Present mode there. What are you trying to? All right, let's get started.
Okay. You want to close the door or something? Oh, yeah. Thanks. Okay. Okay, hey folks. This is on the Linux kernel random number generator, known as random.c. Don't know me, I'm Jason Donenfeld, the X24 Online. Mainly I do security stuff, some crypto stuff, but been doing kernel development for a long time. Been working on WireGuard the last couple of years, where random numbers play a really important role in the crypto. So this year I've put a lot of work into trying to improve the Linux random number generator. So just some background, the Linux random number generator, it's in random.c, which is really old code. It dates back, as far as I could find, to version 1.3.30. I mean, it's really ancient code. There's a copyright date on it from 1994. So I think that even the code was living someplace else before there. But actually, considering when it was written, it's not so bad. It's held up remarkably well, despite the knowledge that was around in that time. And I think for all intents and purposes, it's okay. It's held up. It's been done with some reasonable intelligence. But still, over time, there's been a lot of complexity added to it. So there's different code styles, old code styles, and weird types. It looks strange. And there's also been a lot of conflicting ideas about what the goals are for it, what the various semantics have been. And over time, these ideas have changed, as ideas do, but kind of in one code base. And so things have gotten a little bit jumbled. But you know, most engineering projects are like that. It's practical code that needs to live and work and deal with the challenges of the time. And so it's evolved, but it's old. So just to give you some old idea, an example, at some point there were some performance concerns that led to replacing MD5 with a linear feedback shift register, so like some linear function. Now, interestingly, the original notion of using MD5 as a cryptographic hash, actually a pretty good idea. It wasn't known at the time that MD5 was broken, but as an idea, this was kind of started out nice. But at some point, this LFSR was introduced instead, and then tweaked over the years. And then LFSRs were kind of added all over the place at different points in time for different purposes, which in some sense are fine, but also we can do better just by using a good hash function these days. So when I first saw this, mixed pool bytes, the question is like, what is this code doing? But then my next thought was actually, can I break it or do some funny business with it without even thinking about what it is, about having to use my brain? So I hooked it up to an SMT solver. Rather than having to think, I wrote that same code in PYZ3 that can output SMT2 code. And then I gave it to Boolector, which is a super powerful SMT solver. And then I gave the pool some inputs to control its state. And the question is, can I give it some more inputs to zero out the state or to do something nasty to it? Now, there's some question of what that attack even corresponds to, like what security model that really makes a difference. But just wanted to see like how malleable is this without actually having to think about the code. And so, you know, that's Python Z3 like stuff, and it looks pretty much like the C. And I put that in the SMT solver, and then it spit out an answer really fast. So that was cool. Without even thinking about the code and what it's doing, I could get SMT to solve it for me, which is probably not good for how malleable it is. But it's LFSR, which means it's a linear function. So with some linear algebra, you can just kind of solve it immediately. Because really what's happening with that big code is you have some matrix A and a state vector S, and you multiply the state by the matrix, and then you add in your new input, and that gives you the new state. And because A, the matrix is linear, you can invert it, and so you can move forward and backwards, and it's really a super malleable thing. And so a Magma linear algebra tool could solve the rest just as easy. But this whole thing about LFSR has reminded me. In OpenBSD, there's some curious stuff. A long time ago, the Linux LFSR was selectable. So you could choose how big you wanted it to be, how much state, with the biggest one being like 8 kilobytes of state, which is pretty huge. And at some point, Linux did away with that. But at another point, Linux added this twist table, which is like an extension field on the CRC32 polynomial, which was added for kind of more strange reasons that were relevant during the time they were added, but that maybe aren't so much so now. And so that's some old Linux code showing the old polynomials and the old code. And then there's an OpenBSD. It's like the same code. It's like they copy and pasted it and just chose the biggest polynomial. And then they also used that CRC32 twist table as well. But there's a problem, which is that even though the polynomial is primitive in its own, it's not when used in that CRC32 extension field, which means we can just factor it. So I've typed it up in Magma. There's the extension field, and then we have a polynomial ring, and then we factor them together, and bam, we get the factors that come out of it, which shows it's not primitive. In fact, there's like a x to the 31 term in there, which means there's some pretty small cycles. So maybe this means you can fix the OpenBSD random number generator in place, only giving a couple values. I don't know, but not good. Anyway, this is just to kind of indicate that with these old things like LFSRs, there's a lot of mischief you can do. It's maybe it serves some goals at one point, but like nowadays, why don't we just use a cryptographic hash function? So there's kind of all sorts of things like this that were interesting considerations at one point in time in Linux RNG code, but now we can do a lot better with just kind of simpler things. But all things considered, the old code was fine, but we can simplify and improve it. So let's talk about how things work now and how we got there. So there have been a couple attempts at kind of wholesale replacement at the Linux RNG, except massive replacement generally isn't how Linux development is done. It's difficult to review, people's feathers get ruffled. And so the approach I took over this last year is more incremental, where every change I make is a small change with a highly documented commit. And I've done a lot of code archaeology. Everything I've changed, I wanted to know exactly why the original code was that way. What's the history behind it? So that everything's incremental, but it's also robust. I'm not just throwing things out because I don't understand, what's this, get rid of it. No, I really want to understand why it's there before changing it. But it's been a big project. It's been 147 commits. And if you just look at the commit messages for those, that is since December of last year, it's like 18,000 words of just explanation and gobbledygook. But as a result, random.c is pretty small now. It's 900 something lines of code and almost 500 lines of comments. So it's getting smaller and more manageable. And the goal is for it to be secure and robust while also looking trivial, approachable, not really a big complicated thing. All right, let's dive in. There are several components. how this works. And so we'll start with entropy collection. So we mentioned the LFSR, but now we just use Blake 2S, which is a fast cryptographic hash function. It's fast on all sorts of different CPUs. And it's cool. It can act in a hash mode, like a traditional hash function, or a PRF mode, which is like HMAC or something similar to that, where it's a hash function that takes a key. And internally, Blake basically just hashes that key as a first block separately to have some domain separation. But it's nice to think of it sometimes as a PRF like that. So when we get these inputs from various entropy sources, instead of all this LFSR stuff, we just call Blake 2S update. And we're just constantly hashing things in, which is basic and dumb, but there's a good amount of literature that shows that cryptographic hash functions, computational hash functions like this, are good at collecting, storing entropy. And a hash function is not like a super malleable structure. There's not a lot of mischief you can do with it. So entropy extraction. So the old code called SHA-1 on the LFSR pool, but then it didn't use the whole SHA-1. It actually XORed one half with the other half, which is kind of the same as truncating it cryptographically. Which actually, in theory, that's all fine. It only needed to be non-invertible. And maybe you get something against attacks by truncation like that. I mean, come on, SHA-1 it shouldn't be anywhere in the kernel at this point. So what we do now is first we generate a block of RD-RAND or RDC, whatever's available, as a salt. And I'll talk more about how this is used later. But really, this is just an additional input that that we can use, and we generate it outside of locks this way. So we finalize the hash. This gives us some 32-byte output. And then we do 2 more Blake calls where we use that output as the key for each one. And the input is the RDC block plus 1 or the RDC block plus 0. And then this gives us 2 outputs. The first output then initializes Blake 2S for the next collection of entropy so that we carry forward in some way the old state to the new state. And then the extracted data is that second output. Okay, entropy expansion. So once we get an output from Blake, we have this 32-byte seed, and then we can give it to Cha-Cha-20 and expand this out indefinitely. Cha-Cha-20 is a stream cipher, so you give it some 256-bit key, it's 32 bytes, and then you just get super long stream of whatever. And that's the output that the user sees. But one goal we have is that the RNG has forged secrecy. So if at some point an attacker compromises the system, you don't want them to be able to then look at all the random numbers that were returned in the past. And so usually with something like Cha-Cha-20, you have a key and then like a counter for which block it is. And so if the counter is 16 now and you wanted to figure out what was it when it was 1, you can just wind the counter back, which is bad for forced secrecy. So with this fast key erasure RNG idea, we take the first 32 bytes of the output every time we use it to overwrite that key so that then you can't go back. So very simple, easy to implement thing, and it gets the job done there. Another goal, though, is speed. The entropy collection, there's one pool because entropy is, maybe rare, relatively rare. We don't want to have a pool per CPU, so we collect everything in one place. We get one seed out of it. But when we're actually giving numbers to the user, we don't want to be waiting on locks. We don't want there to be contention, especially on multiple NUMA nodes and all that. So there's a per CPU Cha-Cha instance. So the way this works is we have one base Cha-Cha instance, and this is kind of giving out seeds that go to each CPU. And then each CPU operates on its own, so it doesn't need to take any locks. And this yields huge performance improvements. Okay, entropy sources. There are a couple ways to add things to the RNG. Add device randomness is used for any inputs that might have some randomness, but might not. We don't really know. So for example, DMI tables. Recently there was a patch that was very cool to call add device randomness on the serial numbers from SD cards and MMC cards. On some embedded devices, maybe that serial number is the only non-deterministic thing they have. Now it's, it's still fixed once it's there, but hey, it's something. And depending on the threat model, maybe that something's the best thing you got. The only thing distinguishing, one embedded device from another. So maybe that's useful, but maybe it's not. It doesn't matter. You can just call add device randomness on it, and it won't get worse. Same thing for USB serial numbers, MAC addresses, even wall clock and wall clock changes. It can't hurt. And so if you're a driver writer and you think that your device you're running a driver for might have some bit of information that's maybe random or maybe unique or maybe secret or whatever, feel free to just add a call to add device randomness. CC me on the patch because I'm curious about it, but it really can't hurt to do this. Unless you're calling in a loop super fast all the time or something, but otherwise, this is something that I think can really help on embedded systems particularly. There's one for hardware random number generators. So there's a whole HWRNG framework, which is a bit messy, but from random.c's perspective, it doesn't matter. It just hands random.c some bytes and some indication of how much entropy is in those bytes and adds it. I just broke the lectern. Oops. There we go. Anyway, it's a private interface between the hardware RNG and random.c. So don't use it from your own code, but interesting to know we have this hardware random number generator framework. So for various pieces of physical hardware that know they have real randomness, we can plug that into. Add bootloader randomness is an important one. And one that I'd like to see a lot more usage. Right now it's used by device tree, EFI, a couple other things. And it gets a random seed from the bootloader or from early firmware. And it runs hopefully super early when Linux boots up. Like in some cases, before the slabs have even been randomized. So it really gets a super early seed. So DTB, device tree based systems can pass this through a property called RNG seed. EFI sometimes has a capability of generating a seed itself, which is neat, using whatever random number generators are available to EFI or a TPM or whatever is plugged into that. But also, we're working now to hook this up with system deboot, which has its own management of seed files where it can pass along a seed through the various EFI chains, and at each level will hash it with whatever is available at that level. In 6.0, the x86 setup data linked list has a thing so that we can pass things over on kexec, which is neat. But also QEMU should be able to pass it soon when you start it with -kernel, so that when you start up test kernels, it immediately has a random seed to work with. Even for M68K for virtual devices, these are usually really deterministic, but now QEMU supports it, the kernel does too. There's a little boot protocol so we can pass random seeds that way. And UML, of course, can call get random because it's running as a user process. And so from random.c's perspective, these all just call into it by saying add bootloader randomness. And so if anyone's working on a weird arc that's usually is not very noisy or has problems with randomness, this is a great way to add a hook if you find something in the firmware or something you can use. Just talked on this yesterday, so I won't go in too much, but We also try to deal with VM forks, that is when a virtual machine is snapshotted, or when it forks into two, or when it's rewound. We still want VMs to have some non-determinism, which is sort of contrary to the whole snapshotting idea. And so there's something called VM Gen ID, where the hypervisor can provide a unique ID and signal to the VM that something's changed. These are some oldies. There's add input randomness, so things improve when you like jiggle your mouse around, which is like very kind of naive, but it works. Handles auto repeat, like if you hold down a key with just like a static variable. So it's naive, but it gets the job done. Add disk randomness for the disk rotations. And we'll talk a little bit later about entropy estimation. But so both of these use some of the oldest current surviving code from the original random.c that's still there. The important aspect, though, is the main input for these, even though it takes the button you press on the keyboard or some aspect of your mouse, actually the real primary input is a cycle counter that uses this function random get entropy. So on x86 it's RDTSC, and on other platforms it's whatever the fastest but also highest resolution cycle counter we can get is, or some other type of monotonic counter. Let's talk about this in a second. But similarly, the interrupt handler also is taking these cycle counters, and this is probably the primary, most important source of entropy we have in the kernel. It's triggered more often on most platforms, but also it runs in hard IRQ context, so it needs to be fast. So we have something called a fast mix function that doesn't give it to the main pool immediately. It kind of buffers it for a bunch of IRQs, and then eventually sets a work queue to handle it. So the input at each interrupt is 2 longs, and the goal is to compress it down to a state composed of 4 longs. And so the thing we have now is based on SIP hash, but in sort of a sponge construction. Seems to work. There's some half-decent cryptographic argument behind it. It's not as robust as I'd like it to be, so currently exploring using different sponges for this. Kind of concerning, the fast mix function used to be a custom add rotate XOR permutation from an anonymous contributor named George Spelvin. And anytime you have someone rolling totally hand-brewed crypto, especially anonymous identity, I mean, be wary. And indeed, it's not really a great ARX. It doesn't achieve its goal. But over the years, George Spelvin, this anonymous contributor, has made all sorts of kind of awesome things. His mailing list posts are fascinating. I kind of love the guy. I think he's disappeared in past years. But if you're out there, George, somewhere, get in touch. I'd love to talk to you, but I have no idea who you are. Your email doesn't work anymore. I don't know, but if you're out there, please find me. Okay, let's talk about this random get entropy function. On most platforms, it expands to get cycles. On some, it expands to something specific. So like old MIPS are weird. And we, on some MIPS, have to combine 2 different things. But ultimately, if it can't find anything, it'll fall back to the raw monotonic counter that timekeeping knows about, which is sometimes slow. But this is the primary input material to the RNG. It's really important that this be high resolution. So if you're working on a strange architecture that doesn't implement this in a way, please investigate of what your architecture might be able to provide. Having this be high resolution is really very important. Another entropy source that relates to this is what I call the Linus jitter dance. There was some change in the RNG a couple years ago that caused boot up to fail. or to hang indefinitely. And Linus figured, well, instead of waiting for entropy to arrive, what if we could just generate it? And then he made this this function that uses jitter from the cycle counter to generate entropy. It's not quite rigorous. It's hard to point to any really hard science that says this definitely generates good entropic data, but it's not obviously terrible. And so here's how it works: is we take a sample from random get entropy to the cycle counter, and then we've got a timer. And if the timer isn't currently armed, we arm it for 1 jiffy from now. So that's just a normal timer list. And then we add that sample to the pool, to the entropy pool. And then we just kind of run this loop until that timer has run usually 256 times if we want 256 bits of input. But that's not 256 bits of iterations. That's however many iterations it takes for the timer to fire that many times. So usually that winds up being 512 jiffies worth of iterations, which is kind of a long time. And in the meantime, we have the scheduler jumping in to service the timer request, and the timer is touching some of the same data that loop is running. And so there's some potential cache jitter between the two of them. And so maybe this is chaotic enough that this is doing something. Maybe it's complete garbage. We don't know. It's not obviously terrible, but it's something. And as a last-ditch effort, where we really need some entropy from somewhere, maybe this is all right. But again, maybe it's not. So potential research project here to look into this or try and model it or do something. But currently, as a last-ditch effort, it's the best we've got right now. Then, of course, in platforms that support RDC or RDRAND or instructions like that, I mean, it's great because it's coming from a real hardware source where we know or we hope it's good. Though the old code would incorporate it in a way that is kind of eyebrow-raising. Sometimes be giving some output stream and just XOR it into it. There's a lot of kind of tinfoil hat types that thought, well, like, the CEO, the CPU can see what the input is. It can predict. It can generate its own outputs for RDRAND, and so it could come up with whatever values for RDRAND. It's just that when you XOR it together, it's something that it controls, or various kind of concerns like this. So the new code always puts RDRAND through the hash function. So even if the CPU is backdoored, it could, at the very least, do nothing if RDRAND values are known ahead of time. But it's not going to be able to make things worse because the CPU is still unable to compute a pre-image of the hash function. So on CPUs that support this, you can turn it off, of course, if you don't trust RDRAND or RDC, but this allows the RNG to be initialized immediately, which is important. Which brings us to the principal question of the RNG at early boot time: are we initialized yet? So it's important that the RNG has 256 bits of entropy before it generates output. If it, say, only has 8 bits of entropy and then it generates a stream, then you could just kind of brute force the seed behind that stream and destroy the security of it. So we want there to be a lot. Sometimes we get some physical guarantee from like a hardware random number generator, RDRAND or something, where the device manufacturer says this data is always going to be this entropic. And if we choose to trust them, then game over, it's easy. Other times we don't know, like in the case of interrupt timing or jitter or whatever, all we have are heuristics. We're not doing a physical simulation. It's unfortunate to admit, but this is basically the case. We're just kind of guessing. It's maybe there's entropy here. We hope there's entropy here. We'll try and guess if it's any good. And so the kernel RNG does entropy estimation, which is kind of an impossible proposition. Nonetheless, we have some heuristics. So we assume that 64 interrupts or a second of interrupts have 1 bit of entropy. The disk timings and the keyboard events, the mouse events have this really old estimation algorithm where we look at the 3rd order differentials of the timing. And maybe that's all right. It seems heuristically to give decently conservative, but still non-zero results. And then as I mentioned, the hardware RNG is however much the hardware says it has, and so forth. But again, it's an impossible proposition to really do this. So this is just a heuristic. It's not rigorous. But also, it's only really relevant at boot time. And the code that accounts the amount of entropy we have, it's actually static branched out and never used once we hit the threshold of 256 bits. Now, that wasn't true in the past. In the past, there was some concept of entropy being used up or entropy getting worse over time. But this is all kind of rubbish. Entropy never really decreases. Once we have enough, and then we don't need to touch this code ever again. And hopefully the heuristics are an underestimate, where we're being much too paranoid and there's way more entropy than we say. Interestingly, though, the estimation introduces a side channel attack where you can look at how much entropy is currently available as it's going toward 256 bits. And that indicates something about its inputs, because the inputs are these cycle counters. And the estimation is done based on timing. And so by witnessing how fast the entropy avail file is increasing, gives you some information about what those inputs are. So you could argue that the estimation only makes things worse, because to do it well, it's impossible, and to do it at all, you might introduce a side channel. But I think there still might be practical reasons for including it that we'll talk about in a second. There is a kind of a strange thing here where dev urandom for historical reasons, and also get random with grnd and secure flag, they have to supply bytes immediately before it's initialized. They never block. And so here's an attack, which would be before we have enough entropy, user space is continually reading these. And every time a bit of entropy comes in, it brute forces what that one extra bit was. And it keeps doing this over and over. It only has to brute force 1 bit at a time. And if it does this enough times, then it can get the whole state of the pool, and it's compromised. So actually what we do to satisfy dev urandom, having to never block, but also this attack, is we let the first 128 bits influence the state as they come in, because we want entropy to be available and doing things as soon as possible during early boot. But the next 128 bits we buffer. We don't add those till the very end. So at least after the RNG is initialized, we have at least 128 bits that weren't able to be brute forced. And of course, the amount of entropy is only ever increasing after that. So let's talk about some threat models. Two things that people generally care about. There's premature first, which would be, are we giving output before we've accumulated enough entropy? Which allows an attacker to brute force the state at early boot. Do we care about this? Yes, we do. You don't want to generate your SSH host keys with no entropy. This is important. So we consider the kernel state to be compromised when it first turns on, because the attacker knows it. It's all 0 when the computer starts. So we just call that a compromise. Okay, then we've got the premature next, which is a little more complicated. It's maybe a more generalized version of premature first, where the state of the RNG leaks. So it's compromised sometime later, say by like some kind of info leak attack. And then we give new output from the RNG sometime after the leak, but we haven't accumulated enough new entropy, so the attacker can brute force the state the same way as at boot if we give it out too early. Question is, do we care about this? And Linux kernel RNG does not, which is a lot different from Fortuna, where the Fortuna model, which is the RNG used by FreeBSD, by Windows kernel originally, and I think recently Mac does this. The Fortuna model, it doesn't need to count entropy. It doesn't care about estimation at all. It does something with multiple buckets where it spreads things around at different rates with the guarantee that eventually the RNG state will recover from a compromise. But Linux takes a little different approach, different argument, where if the RNG state is compromised for whatever reason, the most important thing is that we start using new entropy as soon as possible, that we recover as soon as possible. It's less important that we eventually recover and more important that we stop using bad ephemeral keys or whatever as soon as possible. Especially because we don't really ever know when a compromise happens. If there's some attack, probably the kernel is not going to know about the attack if it's done right. And so if it does happen, there needs to be a recovery. And in general, if there's an info leak in the kernel and some attacker can read kernel memory, there's probably bigger problems to be concerned about as well. And under what attack scenarios do you have where an attacker can info leak once, but he can't info leak twice? And what scenarios can you not just run the attack again? There are a couple, but I don't know that they're important enough to care about. Anyway, the lack of concern for the premature next, it goes against a lot of academic orthodoxy, but in recent discussions, it seems like a lot of the crypto community has actually come around that this is indeed the kind of more practical approach. And it allows us to keep the code super simple. Fortuna is very complicated to implement, multiple pools and so forth. And this, what we have is a lot more basic and I think a better attack model. But the basic question for the RNG to answer is, when do we reseed? Compromise might happen. We are getting new entropy in our pools. When do we use that entropy? That's kind of the essential question that RNG has to answer. Currently, we reseed every minute, but remember at boot time, we consider the RNG to be compromised by default because it starts at 0. So during boot, we reseed every few seconds, and then it exponentially works up to a minute. So it's a heuristic. Maybe it could be improved. Maybe we can make that even faster, but it seems all right for now. We also reseed after hibernation in case someone pulls your hard drive and takes the state off there, or suspend for similar concerns, or as I mentioned, for VM forks. Reseeding, in addition to getting whatever entropy it can that's accumulating in the pool, it always adds fresh RD-RAN RDCs. So platforms that have that, it's quite nice. And in general, for this fundamental question, the kernel is really in the best possible position for knowing when to reseed, and for knowing what the new entropic inputs are. It's the best, most important place to get this information. There's no other part of the system that can have information as precise as this. So user space RNGs, for example, will always have worse heuristics on when to reseed or where to get entropy, or it'll always lag behind in some important way. And as random.c improves, knowing when to reseed and where to get more entropic inputs is kind of the evolutionary aspect of the RNG. This is the thing that will hopefully be improving over time. Okay, 5 minutes. All right, so talk briefly about user space interfaces. Generally wary of adding new user space interfaces. Compatibility has to be kept forever. It's a big thing. And the current ones been kind of added willy-nilly, have created pain points. There's like a lot of sysctls that do nothing now. But what we have, the current state of them, get random with no flag, waits for the RNG to be initialized. The GRND insecure does not. Dev random waits also. So dev random is like the same as get random with no flags. It didn't used to be that way. There used to be some crazy thing with entropy running out and some approximation of true random number generators. This is nonsense. That's just not there anymore. Dev random is like GRND insecure. It'll give out random numbers immediately without blocking, but it'll attempt to do jitter first. I would like dev random and dev random to be the same thing. That is, I want them both to wait for initialization. But right now, some platforms will still block at boot. So I'd like to be able to improve this jitter entropy thing or bootloader supplied entropy or something so that we can unify these at some point. But for now, dev random tries to do the jitter. If it succeeds, great. Now the RNG is initialized. If it doesn't, well, it'll still give insecure bytes, but okay. But just to emphasize again, all of those functions give the same types of bytes. There's no difference in behavior, at least after the RNG is initialized. Again, there's no funky business with true RNG. It's all just output from cha-cha-20. Recently, now there's no signal interruption for up to page size chunks. So there's a lot of user space code that doesn't check return values. And on various kernels, this was maybe safe, maybe not, depending on the kernel version, how big the read was. Now we allow for a page size before getting an interruption, which is nice. There's been some recent discussions about trying to accelerate get random in the VDSO for glibc usage. I guess we probably don't have time to get into that now, but we can talk about that after. But with all this, the documentation really needs to be updated. So hopefully I'll be sending some patches to the Linux man page project. So to wrap things up, last year there's been some nice modernization. There's a little bit more cryptographic rigor, not quite where I want it, but we're definitely working that direction. The code is small, so if you're interested in random.c, I mean, just open it and read it. It's like there's tons of comments, and I've made sure to reorganize things by section, and you should be able to read top to bottom and get some understanding. These boot time issues are really important. The bootloader randomness or getting good cycle counters for jitter. I'd like to work towards some way having solutions across all architectures so we can just kind of get rid of this blocking on non-blocking debate. A pretty neat thing is that these improvements have actually been backported to the stable kernels. So most people should now be running these, which fix a lot of issues we had in the past. I'll be around all week, actually, until Friday morning. I'll be in the hallways, so if you have questions or ideas or weird things you want to throw at me about random.c, please find me and talk. Definitely looking for new ideas, especially on the architecture front. Thanks.
I think we have time for maybe one question before we get started with Ying Huang. Any questions? The big toss here. Oh,
yeah, sorry. Okay, thanks for the great presentation. It's the first time I kind of see the full details of how dev random works. Oops. I was wondering if you know if there's any interface in user space to figure out where my kernel is getting its random sources from. Like, you know, is it seeding from my SD card or whatever else? And sort of getting some insight.
You want a user space interface to determine what?
To determine where the seeding is coming from and what's the current state of the random generator in general, I mean, because like, okay, I can get stuff from WU random, but
Well, so right now the seeds come from all the places I mentioned, plus the hardware random number generator. And the HWRNG thing is its own driver, and you can see what hardware it's using there. But for random.c, it comes from all these sources combined. And if you want to know the state, you can call get random with grnd non-block, asking for a size of 0, and it'll return success or failure depending on whether or not it's initialized.
Right. Okay. But there's no sort of like way to get insight as to where currently my numbers are seeded from, I guess.
No, I mean, there's no real-time thing where it's going to say, "Ooh, got a piece of entropy here, got a piece of entropy there." And in fact, if it did too much, maybe that would even be some sort of side channel.
Sure.
And it's just not necessary. It's all the time hashing in these cycle counters, any place you can get it.
Thank you.
Another question?
I think we're about out of time. Is it quick?
Okay, well, find me
afterwards. Thanks again, Jason.
Hello, can you hear me?
Just bringing up your presentation now. Here we go. I guess we can.
Hello, can you hear me?
Yes, go ahead, Ying.
Great, thanks. Hello everyone. Today I'd like to talk about how to manage and optimize system with multiple memory types. The community has worked on the system with multiple memory types for years. Here is some updates in the last year. The basic support for the neural balancing-based promotion has been merged by upstream. The hostage selection of promotion is in unstable. Anish from IBM contributed the explicit memory tiers, and it is in unstable now. Anish from IBM and we from Google is working on memory tiers user space interface. Part of it has been merged by stable. Johannes from Meta sent a parasite to interleave the memory allocation among memory tiers. My colleague Feng is working on respect NUMA policy of CPU set in demotion. My colleague Tim is working on partitioning a type of memory among C groups. Today I will discuss some of them in this presentation and want to get your feedback for them. Yeah, initially all memory are just simple DRAM. Then we get remote DRAM. That is, the memory system become non-uniform. So we use a set of Neumann mechanisms and API to manage and optimize the system. For example, we use Neumann policy and the CPU set to manage page placement during allocation, and use Neumann balancing to reduce the remote DRAM accessing. Then we get PMAM. We put them in separate Neumann nodes so that we can take advantage of the existing Neumann mechanism and API. In addition to use the existing Neumann mechanism API, we also extended them for the new requirement of PMAM. For example, in the default default memory allocation fallback order, the local PMAM may be preferred over the remote DRAM to reduce the cross-socket traffic. But the performance of remote DRAM may be better than that of local PMAM, and some workload may need that. So a new mechanism, Neumann policy, M policy preferred many, is added, where multiple node can be specified as preferred. With that, we can prefer the remote DRAM over the local PMAM for some workload. To optimize the page placement, we will demote the cold DRAM pages to PMAM and promote the hot PMAM pages to DRAM. The demotion support is based on the per node page reclaiming. When there is memory pressure in the DRAM node, instead of discarding the identified code pages directly, we will try to migrate them to PMAM. The promotion is based on the Neumann balancing. Neumann balancing can reduce the cross-socket memory accessing, where identifying remote accessed pages and try to migrate them to the local node. Well, because all the PMAM accesses will be considered remote, so Neumann balancing can be made to migrate the recently accessed PMAM pages to the DRAM. We also implemented a mechanism to select the hot pages before promote. Now, even more memory types of memory are coming. For example, the HBM, high bandwidth memory, and the CXL memory devices, and so forth. How to manage them? Firstly, we will put them into the separate Neumann nodes, so we can use various Neumann mechanism and API for them. In addition to putting them in separate Neumann nodes, to manage more and more types of memory, we want to introduce a new concept, memory types. In general, a memory type is a set of memory devices. These memory devices are unlined by the same driver, linked to the system in the same way, and built with the same media and so forth. So they will have the same performance. For example, the memory type of all HBM node of a system can be HBM. If some CXL devices are plugged in the local CXL slots, where a shared CXL memory pool is linked to the system where some CXL switch, their memory type will be different. Because they are linked to the system in quite different way. Because of that, their performance will be quite different too. Memory types are not just concept. We will use a data structure to represent the memory types in kernel explicitly. To characterize the performance of a memory type with one performance metric, we introduce the abstract distance. This is inspired by NUMA distance. As you know, the NUMA distance describes the distance or access performance from the CPUs of a NUMA node to the memory of the same or another NUMA node. Well, the abstract distance describes the distance or access performance from the CPUs of in a socket to a type of memory in the same socket. That is, the NUMA topology isn't considered to determine the value of the abstract distance. Like the NUMA distance, smaller value means better performance. As you know, the latency and the bandwidth are the most important performance metrics of a memory device. So we want to reflect both of them in abstract distance. The question is how to combine them. We have no perfect solution yet. One possibility is to define the abstract distance as the latency under the expected access throughput. As shown in the figure, if the access throughput of a memory device is very low, the actual its actual latency will near the idle latency. When the access throughput increases, the actual latency will increase too. If the access throughput near the max bandwidth, the actual latency increase rapidly. So, if the access throughput of a memory type will near its max bandwidth, its abstract distance should be enlarged to reflect the actual access latency increment. This also means that the abstract distance will be workload dependent. This is just one possibility. Do you have any good idea of how to determine the value of abstract distance? Please let us know. We also plan to expose the memory types to the user space via the sysfs interface. With that, users can find out how many types of a memory in their system, the memory type of each node, and the performance of each type of memory. One memory type device will be created for each memory type. The memory type devices may be put in sys devices virtual memory type directory. Although it appears more natural to put these devices in sys devices system directory, like node, CPU, memory, and so forth. But the system subsystem is considered legacy now. The kernel source comments says that the new devices shouldn't be added there. Although sys devices virtual is a choice too, memory types are not just the pure virtual software concept. They are related to hardware. Do you have any better choice? This is a question too. Oh, sorry. For each type of for each memory type device, we can show the name of the memory type. For example, HBM, DRAM, PMAM, CXL MEM, and so forth. We need a way to show the nodes of all Newman nodes of the memory type. For example, where the symbol links to the Newman nodes of Newman node system devices. We will show the default abstract distance provided by the driver, and we will provide a knob for users to override the default abstract distance. For example, where the abstract distance offsite read for attribute. This can be used to deal with some problematic firmware, and as we discussed before, the abstract distance may be workload dependent. Users may need to adjust the abstract distance of a memory type to reflect the actual latency under the expected throughput. Yeah, we may also show some raw performance metrics such as idle latency, max bandwidth. These can be gotten from ACPI HMIT or CXL CDAT and so forth. Memory types are used to describe the various physical properties of the memory devices. For example, suppose in a system, even if the latency and bandwidth of PMEM and CXL-MEM devices are similar, they will still be regarded as two different memory types. Because they are different in the way to link to the system, and they're different in media. Yeah. So and so forth. But from performance point of view, users may want to deal with them in the same way. Memory tiers are used for that. As in the example figure, PMEM and CXL-MEM are put in one memory tier, tier 2. That is, memory tier is more about performance. Other physical properties are not considered. Each memory tier corresponds to a range of abstract distance. It includes all memory types whose abstract distance is in the range. Memory tiers can also be used to apply some user policy. For example, although the performance of HBM and the DRAM is different, some users may want to group them into one memory tier. For example, because their workload may run better with the simplified memory tiers hierarchy. Just example. This can be done where customizing the abstract distance range of the memory tier. We want to expose memory tiers via sysfs2. One memory tier device is created for each memory tier. The memory tier devices can be put in sys devices virtual memory tier directory. For each memory tier device, we will show the list of nodes of the memory tier, the symbol links to the memory types in the memory tier, and the start and end of the abstract distance range. We will also provide a symbol link to the memory tier of the normal DRAM in the parent directory. And memory tiers can be used to apply some user policy to group memory types. So we need to provide some knob to customize the abstract distance range for that. We can divide the abstract distance space into equally sized chunks. Each abstract distance chunk corresponds to 1 millimeter. Then we can customize the abstract distance trunk size to change the abstract distance range of millimeters. Yeah, so on the other side, as we just talked, we have already provided a way to customize the abstract distance of a memory type. So with that, we can move a memory type from one memory tier to another memory tier, so that we can use that to apply user policy to group memory types too. Yeah. For memory tier device ID, we have several choices. One choice is to use 0, 1, 2, 3, and so on. This is intuitive to understand, but the IDs will be a little unstable. For example, if there is only one node in tier 1, when we offline that node, the old memory tier 2 will become memory tier 1 now. Another choice is to use the abstract distance start dividing abstract distance trunk size, or abstract distance start directly. In this way, the IDs it will only change if we customize the abstract distance ranges. We can still get the relationship among memory tiers where sorting the IDs. Yeah. Yeah. Here, now I have finished the introduction to the multiple memory types management from management side. So what do you think about solution? Any comments or questions? Yeah, I think some it is still under discussion, or yeah, not finally finalized.
Okay, ready for questions, Ying?
Yeah, in this part, I think it is the alternative for question. About this part.
Hey, so I have a comment regarding the term memory types. I'm not particularly happy about calling CXL memory a memory type. It could be like HBM attached via CXL, it could be PMEM attached via CXL. You might want to find a different way of describing what type of memory it is, if it's relevant, and how it's attached. Maybe there is a better way of abstracting that compared to just throwing everything into the CXL box. That's my personal opinion.
Yeah. Thanks. Yeah. So the figure is misleading. In fact, yeah, if something different, the CXL box in the figure maybe several different memory types. Yeah, as you said, it could be sector attached HBM, or sector attached PMEM, or local sector, remote sector. Yeah, it can be several sector memory types. Yeah.
I had a follow up on that. I think it's more of how close it is, like, or where it's attached, right? Like, because you can have direct attached DRAM or direct attached PMEM on the DIMMs, right? Then CXL, you could have persistent memory there. And in the end, do you really care whether it's CXL or PMEM? It's more of whether it's volatile or not. and the latency adder from there, right? I feel like you could abstract that and just get rid of the whether it's CXL or not, right? It's really about the properties of the media and how that relates to the CPU. But that's just my thought.
Okay. Yeah, I think we can take all the information into account. For example, the CXL may have some specific driver for it, so we can identify the CXL devices from the direct attached devices. And yeah, in the CXL driver, you can further define multiple types of memory, and yeah, something like that.
Yeah, again, following up on the same thing, it feels like an ABI that we're going to introduce, we're going to discover it's not flexible enough. Perhaps some of the things that have already been raised. Maybe it's a question of splitting it up into finer grained things. So have one thing that describes the media, maybe another thing that describes something about how it's attached, or take the easiest ABI and get rid of it completely. Don't have a name and just rely on the properties.
Yeah, Ying, I think you're trying to describe there a way of grouping a bunch of new nodes together. And we already have a bunch of the raw data there that describes what those nodes are and some of how they're connected. So I think what people are saying is that it sounds like the argument to construct those into a bigger bubble, like to group a bunch of nodes together, that argument I think was could be strengthened from that presentation. We're not seeing the argument there to really create those types and enforce that as a policy that the kernel is kind of keeping around.
Okay. Okay.
Okay, I guess you can go ahead, Ying. Thank you.
Okay. Okay. Thanks. Thanks a lot for your comments. And yeah, let's go on. Yeah. In the context of memory tiers, the system default memory allocation fallback order is roughly from fast memory tier to the slow memory tiers. In this way, we can take full advantage of the valuable fast memory capacity, and in some workloads, the hot pages may be allocated first, so will be put in faster memory. But this only works well if the access throughput of fast memory is much less its max bandwidth. That is far from being saturated. Otherwise, if we run some very memory throughput heavy workloads, such as some AI workload, as we discussed previously, the actual length of the fast memory will increase greatly, but the memory bandwidth of the slow memory may be underutilized. So for this kind of workload, one solution is to interleave memory allocation among memory tiers to maximize the memory throughput. Like the interleave NUMA policy, the slow memory pages will be allocated even if there are still enough free space in the fast memory. But instead of interleaving among memory tiers evenly, the proportion of memory allocation will be determined by the memory tier per memory tier interleave weight. The interleave weight for each memory tier can be set according to the expected access throughput of the memory tiers. The interleave weight can be specified via the memory tier CSFS interface. For page placement optimization, the demotion implementation was based on the explicit memory tiers. The code pages are demoted tier by tier. the demotion target is determined from the memory tier information. The Newman balancing-based promotion wasn't changed much yet. The hot pages are still promoted from the lower tier nodes to the nodes with CPU directly. That can be revised to promote hot pages tier by tier too. We may do that after the requirements are more clear. Memory tiers are orthogonal with sockets. The memory devices from multiple sockets may be put in one memory tier. During demotion, although we will prefer the local socket by default, sometimes we may still demote to the remote socket. If we want to avoid cross-socket memory accessing as much as possible, we need to use some explicit Newman policy or CPU set. And we need to respect them during demotion. This is needed to enforce some page placement control policy too. For example, if we want to run some workload in DRAM only, we can explicitly ban the memory of the workload in some DRAM nodes. And we should not demote the pages of the workload from the DRAM nodes to the lower tiers. For CPU side, if C group V2 is used during demotion, the placement control policy can be gotten via the unified C group hierarchy. For each page to be demoted, you can get memory C group, then get the CPU set configuration from through the unified C group hierarchy. But if C group V1 is used, because there is no such thing like unified hierarchy, we don't know how to get the CPU set configuration. If anyone know how to do that, please tell us. For VMA Newman policy that is set with MBAN, we can get the page placement policy via reverse mapping. That is RMAP. But for task level Newman policy, that is set via set Newman policy. We don't know how to get the placement control policy. During the demotion. Not all information is available during the demotion. We can only do our best. From the page, we can get the mapping VMA through the reverse mapping, then the struct, then the owner task, then the Newman policy of the owner task. This doesn't work perfectly for multiple threaded processes with thread-specific Newman policy, but at least it can deal with some common cases. For example, run a workload with Newman control. We have done some performance evaluation for the memory tiering page placement optimization solution. The tests was done on a 2-socket server with DRAM and often DCPMM. If PMM is used, the DRAM to PMM ratio is 1:4. 3 configurations are tested: base, optimized, and DRAM. In base configuration, DRAM and PMM is used, and demotion and promotion is disabled. In optimized configuration, demotion and promotion is enabled. In DRAM configuration, we use DRAM only, but the total memory size is same as that of base and optimized configuration. This can be used to get the best possible test results as a reference. So here is the test results. In the figure, all test results are normalized to make the score of the base configuration to be 100. From the test results, we can find for the micro benchmarks such as PM bench, FIO, the benchmark score of optimized configuration increases considerably compared with that of base configuration. This shows the effectiveness of the page placement optimization solution. For Redis in-memory database workload, the benchmark score of optimized configuration increases about 12.2% compared with that of base, which is close to the score of DRAM configuration. That is, if we replace quite some DRAM with PMEM, the performance is almost the same. But if we increase the load higher and higher, the performance gap between the optimized configuration and the DRAM configuration increases too. We think this comes from the raw performance difference of the underlying media. For MySQL benchmark, the benchmark score of all three configurations are almost the same. Analysis shows that the bottleneck of MySQL is disk random sync write latency. So the memory performance isn't so important here. This also shows an opportunity to use low performance memory for some workloads too. So we have implemented the basic support for the system with multiple memory types, but there are still quite some gaps in this area. Here is an incomplete list of to-dos. We need to finish the memory tier user space interface because this is kernel ABI. So more review. So I will ask for more review here. We have implemented the framework of the explicit memory tiers, and in the next step, we will build memory types from various information, like the driver information and the ACPI, HMAT, SRIT, and so forth. Now we can promote anonymous and mapped file cache pages, but the mmat file cache pages promotion is still lacking. We need to try to find some way to control the page demotion promotion thrashing. And during demotion, we should avoid to reclaim too many reclaimable but unmovable pages, such as inode, dentry cache, and so forth. Yeah, now we only promote hot pages after they have been accessed. But we may try to find some way to promote ahead of accessing, just like read ahead for disks. And there may be more opportunities to further improve the demotion and promotion algorithm. Yeah, that's all for my presentation now. So any question, comments?
Thanks, Ying. Any questions for lunch?
Hello. I have a question about the performance evaluation thing. If you can go back to the slide.
Okay.
Yeah, I wanted to ask, for example, in Redis, what is the memory consumption or size of the workload you are using? And whether it differ with the small sizes that don't trigger demotion and promotion compared to like bigger sizes, bigger memory sizes that trigger promotion and demotion?
Yeah, we as I said, in the system, we the ratio between DRAM and PRAM is about 1 to 4.
Okay, so
yeah, and the 80% of the total memory size is used as the workload size. So quite some
okay, so
PRAM will be used. Yeah.
So have you tried to run, for example, a workload that has the demotion and promotion enabled, but it doesn't trigger any demotion, and measure whether this has an overhead or not?
Yeah, I haven't did her yet. Yeah, I know your concern. Yeah, the neural balancing may trigger the hint page fault. And the page table scanning that will trigger quite some overhead for the
Yeah, because I
but
have done
this
some,
is yeah, this
yeah,
is quite workload dependent. I think. Yeah, for some workload, yeah, you can observe the lengthy jitter caused by the page table scanning or something like that. Yeah, but I have no data now. Yeah.
Yeah, so I have done some analysis and evaluation on the patch set on that, and I have noticed that there is an overhead if we don't trigger demotion, especially with the smaller size. But the performance is better when you have a high workload and higher memory consumption that trigger demotion and promotion. So this is
yeah.
yeah. Thank
Yeah,
you.
yeah. I think so too. Thank you.
Hi, I'd like to go back to the question of that distance function. So how we define near versus far and the complexity of that. That feels to me an awful lot like a policy decision. It's something that's going to get tweaked. Those offsets are going to get heavily used because people want to optimize their particular database. Is it something where we can just not put that distance function in the kernel at all? So allow those just to be written in a similar fashion to you did for interleave weights. Make it something that's entirely user space with no defaults, so we can't get them wrong.
Yeah, so at least we will provide a way for the user space to customize it. And if we do not provide any kernel default value, how do we deal with that? Treat all memory equally? Do not try to do something reversely correct or something. You know that the DRAM is the performance of DRAM is better than the Optane DCPMM. So at least we can provide some default value to make to let user know the DRAM is fast.
Yes.
Do you
I mean,
agree?
another way to look at this is to make it a problem for the distros. So the assumption is, yeah, you need to have some default values in there. The question is whether they are created by a distance function in the kernel or it's considered too complicated. And we push it out as a policy decision.
Yeah, we think it has policy side, and yeah, we think we may need to provide some ways for users to customize it. Yeah.
It's not so much policy though as it is accurate metrics, right?
It's an impossible metric because you've got the high dimensional space and you're trying to flatten it to 1. So.
Oh yeah, if you're yes, the
Well,
projecting down to a narrow dimension space. Yes, yes.
Yeah, I mean, the one thing that we've kind of glossed over in the kernel for now is things like HMAP provide the ability to give you not just latency and bandwidth, but to give you latency and bandwidth with a certain number of other characteristics. So you can have multiple values. And it starts to get really horrible because it depends, are you under load? Are you not under load? Is it sequential?
Yeah, yeah.
All of this stuff. It's tricky.
Yeah.
But, I mean,
Well,
having
we
a
found
Sorry.
we found it hard to deal with that too. So yeah, I want to ask for does anyone have better idea than us? So yeah, we can work on something reasonable or something.
Well, we're at time, so thank you, Ying. And everyone's released to go eat.
Can you hear me? Oh, great.
And then can you, yep, you can. I can hear myself.
That's great. Okay, I think we should get started. Good afternoon, everybody. And my name is Song Liu. We got David Vernet here. And this is also our work together with Rick Van Riel, who unfortunately cannot join us today. We are all software engineers working for Meta, aka Facebook. And today we want to talk about our experience with using kernel live patching at scale.
All right. So we're going to be going over a few things. Start by talking about the existing options for applying kernel fixes, go over some of the history of how kernel fixes in the past and still the present, obviously, were applied when there was an issue that needed to be fixed. So of course, the canonical thing you can do is apply a fix via a full reboot. So quite involved. Of course, you have to install a new kernel, do a full reboot. The kernel is then loaded via the bootloader or UEFI firmware, however you configure it. And then the kernel itself does a full boot, initializes all the subsystems, powers on all the devices, etc. So full reboot is great, but it's really slow. So obviously the positives are you get post checks, power on self-test checks, so you have more confidence that the hardware isn't buggy, there's no issues you have to worry about with the hardware. It's also simple to boot from a power off state. The devices are powered off, the host state hasn't been corrupted yet, hopefully never will be. There's no running tasks, so it's a simple model for applying fixes. The cons are, of course, that you have to migrate everything off of the host, and post checks can be slow. For really large hosts, they can be super slow, sometimes even on the order of hours. And then once it finally does power on and the kernel is booted, you have to rewarm all the caches. So even when you migrate all these workloads back to the host, you might have some tail latency issues. Things might be a little bit slower than you want them to be, obviously. So to mitigate this, we invented something called kexec. Kexec is like doing a full reboot, but you don't go through the post checks. You don't do a power cycle on the host. You install the new kernel, you kexec into the new kernel, which means that you power down the kernel, kill the devices, power down all the, kill the tasks, power down all the devices, load the new kernel image into memory, and then reboot the kernel just as you would for a full reboot. So of course, that's faster than doing a reboot. You don't have to go through the hardware. You don't do the post checks, but it is more complex. You could corrupt things when you do kexec. I'm sure the people that wrote kexec are fully aware of that. And the kernel still, but it's still simpler than doing something like live patch, which we'll explain in a moment. Because the kernel is still doing a full reboot. So all the tasks are killed, all the devices are powered down, and when you reboot the kernel, you're starting from a fresh slate, assuming you haven't messed anything up. The cons are still have downtime. You still have to migrate everybody off of that host. Everything is killed, like I said, so that host isn't usable while it's rebooting. Things are still getting more complex. Like I said, you could corrupt host state, and then you still have to rewarm the caches because you're still rebooting the kernel. Okay, so what is KLP, and what does it solve? Live patching is a mechanism in the kernel that lets you update kernel functions at runtime without doing any reboots or any resetting of the host state. There's special kernel modules, patches, and they're inserted with insmod, just like any other module. And they use ftrace with the IP modify flag to replace the existing kernel function. So it's pretty nifty. Obviously, this is much faster than kexec. It takes on the order of a couple of seconds generally to apply a patch, which is obviously much faster than a reboot. No downtime required. You don't even have to, nothing has to stop. Tasks and run concurrently with live patch. So this is like a really efficient way to apply fixes. The cons are that it's pretty complex. You have to deal with the system with live tasks. Workloads are running that your customers are using. And so if something goes wrong, the workloads that were running on that host are going down without having been migrated. It also requires not a lot of, but extra engineering work that you don't have to worry about with something like kexec or reboots. Not everything can be live patched. You can't live patch data, even though live patch has a mechanism called shadow variables that let you provide a mechanism for sort of updating data in a safe way without actually patching, global data in the kernel. Even if you have a patch that's correct, you have to look at it really carefully. if you look at the ecosystem, the tools that are available in the ecosystem, which Song will talk about, all sorts of warnings are sprayed everywhere saying like an expert needs to look at this. If this breaks, it's your fault. You really need to know what you're doing. And then even if a patch is actually live patchable on its own, you sometimes have to finagle things because there's just limitations in what you're doing when you live patch. It's hand wavy, but extra work is required is the highlight. So just a little bit of an overview of how live patch works, at really high level, skipping over some details here. But at the start of most functions in the kernel, we have the snop instruction, which we can overwrite with a direct call to an ftrace handler. And then in the ftrace handler, there's some logic that checks to see whether the patch has been fully applied. And if it has been fully applied, which I'll explain what that means in a second, you call the newly patched function from every task in the system. And if it hasn't been fully applied, it checks to see if the task is finished migrating to the new patch. Migration means that the task is no longer running the function being patched anywhere in its call stack. And if that's the case, the live patch subsystem marks it as patched and safe to use. The reason that that's necessary is because you don't want to call a function that's being patched if it's higher in the call stack. Functions are there for a reason. If the semantics of that function change, maybe you change how locking is done, maybe you change what kind of corner cases you're looking at to decide if you need to lock, you can end up deadlocking or causing all sorts of problems. So you have to wait until you're not calling it anymore. Finally, once every task in the system is transitioned, this unlikely branch here is no longer hit, and you always take the newly patched function. So there's a little bit of overhead because you're always using this ftrace handler. Going back to kind of some of the limitations of live patch, you probably don't want to do like a patch on the spin lock implementation because now you have a lot of extra logic happening in what's supposed to be a very hot path. And then the ftrace handler stays registered indefinitely until the patch is either replaced or removed, if that's what you choose to do. Okay, so Song?
Okay, so I would like to give a quick overview about the existing live patch ecosystem. So KLP or live patch is very common among people called enterprise distros. And the primary goal, as people understand, is to want to fix bug without rebooting or without even stop your workload. And there are very well-known ones. There's a K-patch from Red Hat, there are K-graft from SUSE, and K-splice from Oracle. And I would like to take the chance to thank Red Hat folks to share K-patch toolchains and supporting these tools. That's very helpful in our work. And there are also third party who build like patches for public CVEs for publicly available kernels. And as far as we know, all these different flavors of live patch use the similar in-kernel mechanism. Okay, now how do we and why do we use KLP at hyperscale? First, we want to roll our fixes faster. At the hyperscale, we don't have any problem rebooting one machine, but to reboot every machine is a totally different story. First, at hyperscale, downtime is not an option. Facebook never go down, otherwise people are gonna call the police. And therefore, we have to do the kernel upgrade in a rolling base. You have to migrate your service to a different service because different server because you can reboot this server. And as a result, our typical cycle to upgrade the fleet is in the order of weeks. And of course, that's not fast enough for critical urgent issues. And on the other hand, with KLP, we are capable to roll the fix much faster. Another case we found with KLP is that they are very helpful to debug the most tricky issues. Nowadays, like in the kernel, we have very good tracing tools like BPF, ftrace, perf. However, we will find the cases that tracing is not very straightforward. For example, you only want to trace one condition in the middle of a function, maybe after 3 if. That's not easy to create a trace for that. However, if you use KLP, you can put a print K or maybe a traceable function at the exact location you want to trace. Another case is when we find there's some error condition is not easy to reproduce. And if you want to change some logic that either require reboot or even reload the module, you may destroy the reproduce, and you may take you hours and on many machines to get you back to there. However, with KLP, we will be able to turn small things and try with exactly same reproduced scenario, and that will speed up our debug many, many times. So now how we use it. We try very hard to enforce homogeneous configuration. What does that mean? That means the user cannot decide which fixes they want. We have control. Okay, this is this kernel. You should run this kernel with this set of fixes. And the other side of this requirement is a promise from the kernel team say, hey, we're going to promise the KLP will not do anything bad. Which, in other words, we don't want anything that is good for certain workload, but it's going to hurt for other workloads. So with this promise and this requirement, we will be able to do something called a cumulative patch. What this means that we combine all the fixes for one kernel into one KLP module. These have multiple benefits. First, we greatly reduce the test matrix. Every patch attached alone, we just need to test everything alone. And the kernel provides some very nice feature with the replace flag for the KLP, which means we can attach a new KLP and detach the old KLP in an atomic switch. And we'll talk about the atomic KLP switch, KLP transition later. And another part of the using KLP at hyperscale is we need the KLP rollout to 100% managed by automations. What we do is we pack a KLP module into our RPM file, something like it's a KLP for kernel version X, is the hotfix Y, which is the versioning we have for the KLP. Then we manage the KLP rollout just as we manage any other RPMs. And we use our health check built in the infrastructure to help the rollout of the KLP. What it looks like is that we compile the kernel metric with the new KLP versus the same kernel with the old KLP or with no KLP if this is the first ever KLP for this kernel. And we check for new crashes, increased failure rate, or unusual KLP transition failure rates, and etc. And if any of these metrics look bad, the automation will stop the rollout and set alarm for some human being to look at the issue. So the result, KLP has helped us a lot. Right now, we have millions of servers running with KLP all the time. Typically, we roll out a new KLP in the time frame of 1 week, which is already much faster than regular kernel rollout. At full speed, we can technically patch the whole fleet in hours. But we haven't seen a case that we really want to do that. And as we use KLP in our work, we found it's essential to keep our fleet healthy. And there's multiple attributes of that. I want to talk about two things. One is like in the past, we used to see, oh, this kernel is bad. We need a fix-only release just to fix a bug. This is very distracting for regular feature release, which usually we push that release to the next number. And in some worst case, we will see, okay, this fix-only release is not enough. We need another fix on top of it. But now with KLP, we eliminate almost all the fix-only kernel release. Most of the fixes, urgent fixes, are shipped out with KLPs. Another benefit is like we no longer debug the same issue twice. As I mentioned, that our typical rolling cycles is in order of weeks, which means if we fix a bug, we ship the fix in a newer kernel, it takes weeks before the whole fleet to get the new kernel. And it's totally possible another team will hit the same issue in a different, condition. And with KLP, we'll be able to roll the fix soon enough that we don't have to debug the same issue twice because it's already fixed in the fleet.
Okay, so now we want to take you through some of the bugs that we've run into and some of the issues we've run into because we're at hyperscale. We've used LivePatch in ways that that have allowed us to find some issues that you probably wouldn't encounter or have maybe noticed at a smaller scale. And I think the highlights I would say is that small performance issues become pretty big problems when you're talking about a scale of millions of hosts. We'll give an example of a bug there. This could actually happen in smaller cases too, but we found that KLP can sometimes conflict with tracing because of that NOP instruction where we register the ftrace handler. If you were tracing that function in other contexts, you have to be careful not to overlap and try to live patch a previously tracing function. And we also observed that there were some transition failures, which is problematic at hyperscale, but probably or maybe not at a smaller scale. So the first bug I want to talk about was a bug that we actually fixed and ended up sending upstream, where we noticed that when we were sending out a KLP, we would see a short but large uptick in missed IO, and this would cause alarms to get set off all across the company. Specifically, we saw that TCP retransmits would bump up. We also saw similar but different symptoms like IO and fsync latency would go up, so we'd have database stalls. Again, lasting for 1 to 2 seconds, really short, the span of the live patch insertion, of course, but across millions of hosts, like everybody, loses their minds and thinks that everything is breaking. So what happened? What happened was the insmod task was hogging the CPU and starving ksoft IRQD. So I'm sure a lot of people in the crowd have run into this problem in one form or another. If you've ever added a conn resched, there's a good chance that you are aware this can happen. So we compile our kernel without preemption with config preempt equal n. So the problem was that when you load a KLP module, you have to do relocations like you do with any other module. And then during KLSIM symbol lookup, we were starving ksoft IRQD because it's a very hot path and we weren't doing a conn resched. So the fix was conn resched, and we eventually upstreamed that. The fun thing is we actually originally, we sent it upstream and then we backported it, but we ended up fixing this in our fleet with a KLP. Because as Song said, we have KLP available to roll out fixes. We use it all the time. We don't want to wait for the next release to be able to roll out future KLPs. So we knew that we were going to see all sorts of alarms go off for a couple of seconds. We rolled out the fix in KLP with a KLP. Everybody lost their minds for a couple seconds, and then it never happened again because we could roll future KLPs out. We don't know if there may be other limitations of where you can apply a KLP. You can't patch the ftrace handler. Obviously, that's no trace. But I haven't been able to find an issue anywhere else in the live patch subsystem where you couldn't patch it. Like even the init module callback, you can't transition a task that has that function in its call stack, so the insmod task wouldn't be able to be transitioned. But eventually that would exit, and then live patch actually asynchronously tries to transition tasks after that too. So I think that would be fine. So it's a testament to the robustness, I think, of live patch that you can fix things with a KLP. But that was one issue that was fun that we ran into.
Okay, so the next, as we work in the hyperscale for a long time, we realize tracing is the first-class citizen in the data centers. So monitoring and tracing, they're as important as the main service, because if your main service is down, people know that through monitoring and tracing. And so no matter which one goes down, there are going to be alarm, wake up people at midnight and look at this. And whoever got woke up will be equally mad at whoever break it. So, and as a result, we need to make sure the KLP, while you fix the kernel bug, should never break these tracings. But unfortunately, we have hit a couple issues. The first one is we found the KLP may break your trace point. The reason behind that is your KLP, when you build a function, this function cannot have jump labels. And what we handle in the toolchain is if we cannot jump labels, because trace point call is a jump label. The two chain will just remove it. And this one shows us as the block trace start missing events. And we spend some time to realize, oh, this is because we are using a KLP to this function, and this function calls your trace point, and it's no longer happen when you have the KLP version of this function. And fortunately, this bug was partially fixed in 5.8 or newer kernels. And this work done was by Josh Poimboff. And by partially fixed, I mean, if this trace point is in VM Linux, then we don't have any problem. This trace point call will not be removed by the live patch. But unfortunately, if the trace point is installed by a different kernel module, we'll have the same problem. So another case with KLP and tracing is like we found KLP may break tracing tools, may conflict with tracing tools. So this specific example we look at is like we have KLP and a BPF trampoline on the same function. And they both use ftrace flag IP modify, meaning we want to modify the IP of this function. And by definition, yeah, we should not have two of them on the same function. Otherwise, who will decide where we go? And the behavior is like the first one wins. Whoever comes late will fail. And this thing we have shipped the fix in the latest 6.0 kernel. And what we have done is, on one hand, we make sure the ftrace direct function, which is used by BPF trampoline, no longer set IP modify. Then we teach BPF trampoline to say, hey, if you are working with someone with IP modify, these are the things you can do to make sure the two can work on the same function. So this one will be released to the world in a few weeks. So the next thing we want to talk about is the KLP transition failures. And recall that we have to, when we apply a KLP, we have to finish this transition. Specifically, we get from this KLP on-patch state to the KLP patch state. And this transition happens for each task. And basically, we need every task to find a transition point. The transition point should usually be two cases. One is the task access kernel space, meaning you're not talking any kernel functions, you can finish the transition. The other case is the task goes to sleep, and when it's sleeping, there's no to-be-patched functions in the stack, then okay, you can finish the transition. As a result, we know there's kernel thread who never go back to the user space. They sometimes fail the transition. Usually the transition, the failure rate is not really high, but it's a low failure rate times a big fleet. This could mean many, many failures. So we have to be very careful. We have to be very careful about them. So here's a real world example we have seen. So we have the butter FS reclaim work that could run for many seconds. This thing runs on the event onboard work queue. So from a work queue items point of view, it's clearly not good. You should free up the queue for others. But if you just look at the thread, it's not that bad because this work can reschedule many times per second. So if there's something else like soft error kicking in, this one will not block that. So we are not going to the first issue like David mentioned. However, because this work will run for many seconds, we're seeing 10 times more increase in the KLP transition failure rate. It's simply because this event unbound work queues, this thread never go to sleep. Unfortunately, this is the case that we cannot fix with KLP because we have tried to ship a KLP with the fix, and we're seeing 100 times more transition failures. This is because even when event unbound goes to sleep, it sleeps with to be patched function in the stack and just not safe to do that at that point. So right now we have a temporal fix. We have this KLP try-switch task in the work queue thread. And it's low overhead enough, but it seems not a universal solution yet. And we are working with the upstream community for a better fix, and we'll talk about that later. So our ongoing and future works. So as we mentioned, like because we have a big fleet, if we hit some small corner cases, that could be a big issue for us. So we proactively try to find all the corner cases and try to fix them before it actually hit us. And here's the example. So we can use KLP to apply fixes to other kernel modules. Everything works fine. You can load the module first or load the KLP first. Either way, you get a patch applied correctly. However, if you have a kernel module with patches, you cannot reload the module. Meaning if you unload the module and try to reload it again, it will fail some sanity check in the relocation address part. This has been a non-issue for years, but it hasn't been a priority for the community because typically unload module is not an operation people are going to do. However, at our scale, we quickly identify, oh, that could be a huge problem. We have a fleet run by automation. We have people run RM mode with automation. We can easily run that on millions of servers in an hour, and later, suddenly all of them cannot work again. So we're actively fixing that. And besides that, we are working on adding new features to the toolchain. Here are a couple examples. One thing we're trying to do is to use clone PGO support to compile kernel, and we see there's a benefit. What it does is take a profile data and put it into the compiler and help the compiler to optimize the code. To build KLP for this kernel, we need a K-patch to take the same profile data as the input. And it's not a dramatic change, and it's almost done. And we are using that in production for a long time. Unfortunately, this part is not upstream yet because the kernel part is not upstream yet. So seriously, I don't know what's the plan with that, but this is the work we need, and it's working great for us. Would you mind keep that for the end? Thank you. And so the next thing we are working at is to build one KLP for both in-tree fixes and out-of-tree fixes. And this is the this requirement comes from that we need a replace flag, which means we cannot have KLP on the one system. So we have to put them together and to get our homogeneous configuration. And this is something we are working right now. Lastly, we are working on reducing KLP transition failures. Here's an interesting idea. We got Peter Mladek. And basically, when we see KLP transition fail to finish at the first time, we use ftrace to attach this try-switch task to specific functions that is blocking the transition. And then the pending task will keep running with all these ftrace functions. And now they will finish the transition without going to sleep. And we're not sure how this is going to work out at the end, but I think it's a very interesting idea, and we have big hope on it. And that's all we have for today. Question? Yes?
One question is, do you also consider patch support for assembly files because some security issues that come up?
So we need a knob. We need.
Okay, now the mic is working. Live patching for assembly files, like there is a .s file, syscall entry path or VM exit path, and you want to fix something there. So we tried doing that. Live patch didn't work. Do you run into issues, and are there any plans of implementing support for that?
I think as long as it's accessible by KL-SIMS and you can register an ftrace handler, it should work. I can't think of any reason it wouldn't. I don't know enough about ftrace to know if you can wire an assembly function to be callable and recognized by ftrace. But if you can, I think it should work just fine. Yeah.
Actually, most all assembly functions don't have the ftrace NOP up in them. So in general, it's not really possible to patch assembly right now.
Yeah, the NOP is the hard requirement, and.
But you could add a NOP in your assembly, couldn't you?
You could. Yeah, we just haven't.
But we need to add a knob, and we need to ftrace to track that. I don't think as long as we can add a knob, I don't think that's physically impossible.
Yeah,
we need
no tracing in entry. Not gonna happen.
No, I understand the concern is that we shouldn't be tracing this stuff, right? But we could mark these as non-traceable and still have a knob there for live patch. These are different use cases, but there is just one knob there, right? And we concerned about somebody's going to attach a trace point on syscall entry or VM exit and ruin their performance completely. I do get that, but sometimes you do need to live patch those places as well, especially like bugs.
Miroslav just mentioned to me on IRC that they once did this by rewriting the IDT and the syscall MSR.
That's cool.
Yeah. It is possible. I wouldn't recommend it. I mean, especially the Facebook. No.
Yeah, there are a lot of creative solutions that you can do, but the more creative, probably the less recommended it would be, or the more careful you have to be.
Yeah, you get to keep the pieces.
Yeah. Yeah.
Maybe one remark regarding the live patchability and non-traceability. The thing is that KLP relies on ftrace quite a lot by intention. So if you separated that, that's a whole nother story.
Question, how big are these modules on average, and do you have stats of, on average, how big they are?
Is the mic work?
This mic is working, yes.
Okay. Sorry, can you speak a little louder?
Yeah, how big are these modules on average? Do you have statistics of how large these files are? I'm just curious, on average, because you're combining all these fixes into one module. I was just curious how big they are.
I think it depends on what you're patching. So if you build a module, usually you wouldn't handwrite these modules. You'd use a system like KPatch build, which Song alluded to. So if you're patching something that's, that's linked against by a lot of people, or it's like inlined rather in a lot of places, it will be bigger or smaller. But I haven't looked at the size of the module personally. I don't know if Song has.
Yeah, I think it's on the smaller side, like I would say smaller than 1 megabyte.
Oh, I was wondering, like lines of code too. Do you know, like on average, like do you guys have stats on that? I'm just curious, not anything.
Oh, lines of code, there's like a supporting logic for the module, and there's actually fix of this module. The actual fix will contain every function you want to replace. There's a new copy of the whole function, and the supporting logic will hook the new function to the kernel. So it really depends on the number of fixes. You get the size. That dominates the size of the module.
Okay, but no clear idea on average size or anything like that.
It's just hard to say because usually you'd use tooling to build the module. It's not like you can write it by hand. And the live patch self-test suite has modules that they wrote to test, applying different types of modules and shadow variables. They're really small. They're like 50 to 100 lines or something like that, depending on what it's doing. But yeah, I mean, like Song said, if you're if you're building a module that's inlined in a bunch of places, or a function that's inlined in a bunch of places, and you're patching several functions, it could get bigger. But you probably wouldn't be writing that yourself. There's a question back there.
That's why I don't do football. Do you guys apply link time optimizations to the kernel? And if so, do you, or even if not, do you have like an idea of how that would affect live patching?
I'm sorry, I didn't get the first part of your question.
Are you familiar with link time optimizations for the from the compiler?
You mean link time optimization?
Right, right.
We currently don't do that, and we do have a plan to do that, and we're aware that could be a potential issue with live patch. That's what we probably going to chase later this year or earlier next year.
Okay, cool. All right, thanks.
Oh. Miroslav, did you want to say something, or did you write in the chat?
Yes, I have a question similar to the previous one. So do you know how many functions do you typically live patch?
Usually we'll, like how many fixes do we include in a single instance of a live patch?
Well, not entirely fixes, but the functions themselves. I mean, because that could have some impact on the whole transition and its performance too.
You probably have more knowledge about that.
So I guess the question is about how many functions we usually patch, and we're in the order of, at the most, in the order of tens of functions, and it's because we just keep building up this cumulative patch, and with the kernel, the first one we'll probably just have 2-3 fixes, and let's go along. Right now we have that's kernel. We call hotfix 10. That's 10 generations of fixes. So, but we never go beyond 100 functions. And I think this also part of the question is about whether that have an impact on the transition failure rate, or I didn't get that part clearly.
Well, okay, so theoretically it could happen that if you patch, let's say, like ordinary core functions quite often, it could have some impact on failure rates. While on the other side, if you patch only, let's say, functions in kernel modules drivers, then it would not happen much, right? So the question was mainly about if you know if there's some distribution regarding this core or driver functions.
Okay, so I get the question now. So yes, I had a similar question before. Is yes, theoretically, with the bigger the patch is, the higher failure rate gonna go. But in our case, we never see that being an issue with a bigger patch. The actual issue happens in two cases. A few cases where there is like, we really have a patch, a thread sleep with the function that we are about to patch. And the other case is like we have a thread, it's not going to sleep. There are actually multiple cases we hit the same. Usually if we get one of these, the failure rate will go 10x or maybe even more, we'll get 100x. But the size of the patch is grow linearly. So usually we don't see a problem with a bigger patch, or there's not a huge hit on the failure rate. Does that answer your question?
Yes, thank you.
So the patches are, because they're binaries, they're specific to a certain version of the kernel, right? So how many versions of the kernel do you support at any given time? Just one? Like just the latest kernel, or do you kind of backport patches to other kernels?
I think we have maybe about 10 different kernel release, and each of them may have multiple flavors at the time. So we have automation for that supports all of them, and just, yeah, so far it's not a problem.
I think we have time for one more question.
I was curious if there's any services that you, oh, sorry, go ahead.
Yeah, maybe somebody that hasn't asked, if that's okay, Luis. Thanks.
So could you, the slide 34,
You might have to click the arrow.
so I'm a little curious on the PTO optimization you applied with the clown. So did you see, do you know how much the performance benefit from it? Do you have any number for that? The PTO?
Yeah, we have some numbers, but I think it's not related to the talk. We can discuss that offline.
Okay, okay, thank you.
Right. Thank you, everybody.
Okay. Can we? Okay, let's start. So hello, everyone. My name is Shakil. I will be presenting TCP memory isolation on multi-tenant servers with my colleague, Christian. And here by multi-tenant servers, I mean server which are running multiple workloads of different properties, different priorities. For example, batch jobs, latency-sensitive jobs. Okay. Right. So we have been working on this project for almost a year, and there have been we have been getting support and help from a lot of colleagues. Some of them are here as well. Yeah. Let me jump next and go over the outline. So first, I'm gonna give more on the background, what exactly is TCP memory, how it is accounted, and then present the problem with the existing TCP memory accounting and our solution. Next, I will go over there. And then deploying, like the challenges in deploying this solution across our whole fleet. And then the remaining more the work in progress and the conclusion. By the way, you can ask questions in between as well if you have any. Okay, so what is TCP memory? So in simple terms, it's just memory holding the packets in flight. For example, in the TX send side, it's memory holding the packets until those packets are acknowledged from the other side. On the receive side, it's memory, again, holding the packets until the application has consumed those packets. So how it is accounted today? So today, we have a global counter, TCP_memory_allocated, which is used to account basically all the TCP memory usage on the system. And you can envision that since this is single global counter, definitely there will be it will be hot, it will be contented. So there are caching mechanism in front of it. Actually, recently we switched the caching mechanisms, and we are going to go over why we did that later slides as well. So yeah, and the second part, how this TCP memory usage is being controlled or limited. So there's a system level TCP_mem, which is exposed to the sysctl. It is an array of 3 integers. So whenever the usage goes above TCP mem2, it starts filling. It's a hard limit. If the usage is above TCP mem1, it enter the system into the TCP pressure state and keep the system under TCP memory, TCP pressure state until the usage falls below the TCP mem0. Now, what exactly I meant by the TCP pressure? So what does the kernel do when the system is under TCP pressure? So first thing, any socket which might be active at that time when the system is under TCP pressure, its send and receive buffers will get reduced to a very minimal value. On the receive side, packets may get coalesced or they may get dropped, preferably out of order packets. And the kernel does wake up the applications. Hey, like we are under pressure, you should wake up the application to consume those packets sooner. On the transmit side, the kernel may throttle the sender, the thread of the sender, to wait until the memory is available. So then it will allow to go and send it. So these are the mechanisms which the kernel does when the system is under TCP pressure. Now, next, I'm gonna go, what are the, like, you can clearly see here, like these mechanisms does not really care who they are impacting. So on a multi-tenant systems where you have jobs of different priorities, the current mechanism basically cause like isolation issues, particularly like since this TCP mem is shared, unregulated limit, it can, like a low priority job can hog the memory and start impacting the higher priority jobs. So whenever system is under TCP pressure, any arbitrary socket, irrespective high priority, low priority, its buffer get reduced, its packet get dropped, any sender, irrespective high priority, low priority job, it may get throttled. So that's the first problem. The second problem is there's disconnect between the system memory and the TCP memory, or more specifically, the system memory pressure and the TCP memory pressure. So giving you example, when the system is out of memory and TCP is in the normal range, we will, like, the kernel will allow network burst to come. And because the TCP is in normal, the TCP pressure mechanism will only get triggered when the TCP memory is under pressure. So now these network bursts can, so system is out of memory, there are many reclaimers working. It can steal, it does steal memory and CPU from all these reclaimers and keep the system in this memory pressure state for long. Since it have access, like these are happened in the software IQ, so they have, they does allocations, many of the structures, struct SOCs, SKBs does allocation with the GFP atomic. They have access to the atomic reserves. They can go and deplete the atomic reserves. And when those atomic allocation failures happen, they may happen for any application, any sockets of any application. So now, at the high level, so first and second problem, you can think of the first one was when the system has memory, but the TCP memory was out of, TCP was out of memory. Here, it's the system is out of memory, but the TCP has memory. So this disconnect between the TCP memory and the system memory is kind of causing the issue. So for now, we are gonna talk more about the problem one, the solution for problem one. For the problem two, we are still working on the solution. We will discuss some ideas at the end. But yeah, let me jump to the solution. Okay, so the solution for the problem one, it's simple. At the high level, you can say, just remove, since this global TCP limit is like unregulated and does not really differentiate, just remove this limit. Let it be unlimited. Now, it can be abused. For that to counter, we have to start accounting the TCP memory of the jobs against their, like whatever their limits are. And usually we use C groups, memory C groups, to provide isolation between the jobs. So here, what I'm saying is like start charging the jobs for their TCP memory. So previously, no one is actually paying or like being charged for the TCP memory usage. Now, so with the C groups, you start charging, and the C groups memcg limits will be limiting their TCP memory as well. All right. So going a bit more in depth of the solution. So C group V1 and V2 provides different semantics how to account the TCP memory. In the V1, TCP memory is accounted separately, is treated as a separate resource. It has its own usage. It has its own limit. The issue here, you can see it is kind of influenced with at the system level, like the existing accounting mechanisms, where TCP memory is like separate from the system memory. So here, the main issue is it adds the complexity to provision another resource across all the provisioning, like stack, node controller, the job scheduler, and the resource planning, everything. And by the way, like for the V1, it is off by default. And my main thing, not assumption, but I think I'm very much convinced that no one is actually using the C group V1 TCP accounting because it's very inefficient. And no one is complaining for the efficiency because networking is kind of very prone to these like charging and counting. So no one is actually using it. So we went with the C group V2, which is C group V2 basically treats the TCP memory as the memory, as any other memory, and it aligns with our like high-level V2 migration plan. So what but we are still like on the V1. So what we actually did was port the V2 mechanism semantics into our V1 deployment and like enable the TCP memcg here. Right. So here, just to point out, like now, what about the TCP pressure, definition of TCP pressure in the memcg world? It's still work in progress, and we will be doing like some discussion at the end of the talk. Okay, let me, so that's the high level overview of the solution for the isolation. And next, I think we are gonna go over the challenges while we try to deploy the TCP memcg across our fleet.
Cool. Yeah, so like Shaquille mentioned, the idea of basically just removing the global limit and charging TCP memory usage to the memcg is fairly simple. But essentially, we're changing how memory accounting works kind of for the entire fleet. So there's basically a lot of challenges in actually being able to deploy this to all of our machines. And kind of one of the first problems is that we don't really have any historical data on how much TCP memory each job is allocating. And basically, if we're going to start charging jobs for their TCP memory usage, we have to have some way to kind of let them know how much memory they're actually using. And basically, we want users to provision for this memory either by raising their memory limits or something like that. And if they do this incorrectly, it can lead to either OOMs or network degradation due to basically the job itself entering TCP pressure. And to make things even harder, I guess, like TCP usage itself is generally very spiky, so it's not exactly a simple thing for users to kind of provision for this resource, even if they have like some idea of how much TCP memory they are using. And kind of on the organizational side of things, from an infrastructure perspective, rolling this out is a kind of a reliability win, and it kind of unblocks some further rollouts. But from a user perspective, we're essentially just asking them to pay for a resource that they were getting for free before. So basically, there's not a ton of motivation from the user perspective to kind of make these changes. And at the same time, like as infrastructure owners, we can't just break user jobs. So we want to basically manage this rollout in a way that we don't end up getting blocked on just a single user, kind of not making the necessary changes to kind of prepare for TCP memcg charging. And finally, I guess this is because this is a new feature, there's always going to be bugs and stuff. So I guess the goal for us was more like how do we kind of find those bugs early and make sure that they don't kind of get us into a situation where we're trying to like roll out this change and roll back the change because we found some bug and basically causing a lot of disruption for users. Yeah, so as far as how we tackled some of these challenges, for the first challenge, basically, how do we kind of know how much TCP memory these jobs are using? We basically implemented a new mode in TCP memory accounting. So basically, it was a mode to measure the TCP memory usage associated with the C group without actually charging it towards the C group's memory limit. And so it's not, I guess, a perfect measure of what would happen once the charging is enabled because like it doesn't take into account like any job specific reactions or kind of reactions getting, of the job itself getting into memory pressure or network pressure, but it basically provides a good starting point for us to estimate like how much network memory a job is actually using and how much additional kind of resources the job would need to provision once we do start charging them. And yeah, so essentially we deployed this measurement feature and started collecting this usage data and providing it to job owners so they could get kind of a preview of what their usage looked like. Yeah, and then so basically, so once we have this data, then it gets into the problem of how do we actually kind of act on the data. And given the kind of scale of this rollout, the goal for us was to kind of have as little involvement as possible and basically automate most of the things that we could. So generally, like for jobs that are under provisioned in terms of their memory limit, we tried to push them towards basically existing Google kind of load shaping mechanisms that are available to users. And there's kind of, I guess, two main ones that are relevant for the TCP MCG charging. The first one is basically user space traffic throttling. So this basically allows users that are taking like requests and stuff to configure their own application such that it will start dropping requests or kind of load balancing requests to other instances of their job when their memory usage gets high. And basically this kind of helps address the spikiness problem of TCP that I mentioned before by basically kind of smoothing out those spikes both in time and across the different instances of user workloads. And the second load shaping mechanism is basically dynamic job sizing. So this one basically, instead of having users kind of set their own resource limits, basically the infrastructure itself will monitor the memory usage of a job and adjust the memory usage limits as needed. And basically together, just by enabling these two mechanisms, basically the users can kind of have a hands-off approach. They don't have to worry as much about kind of tweaking their limit and stuff, and hopefully everything kind of just works. However, like there are some set of users that basically do their own kind of specific optimizations and stuff, and so these previous load shaping mechanisms aren't necessarily an option for all users. And so for those users, we essentially have to work with them to kind of manually change their memory limits if needed. And because it's manual, it's error prone. Basically, like we mentioned before, it's kind of hard to predict exactly what the TCP usage and even what the behavior will be like once TCP charging is enabled. And so, yeah, basically these are the kind of users that are at risk for causing the entire rollout to kind of have a long delays. Yeah, so basically to address like those kind of users that have like basically special circumstances that require them to kind of basically take a long time in order to de-risk this rollout, we essentially opted to implement a fine-grained control for enabling and disabling TCP MCG charging. And so basically in the kernel, it's implemented as like a per C group control, and then we expose it to the user through basically a per job config that basically the user can set, and then it's ultimately up to the infrastructure to decide like whether or not to accept the setting the user requests. And this fine-grained control basically helps us in two different ways. One is kind of opting in, so basically allowing users to manually turn on the TCP MCG charging ahead of us, enabling it fleet-wide. This allows jobs to basically experiment at like a small scale before the actual rollout, and hopefully kind of work through those issues, the potential issues that I mentioned before, in a, I guess, more controlled environment. And then the second one is allowing users to opt out of the rollout. So basically the idea is that because this entire rollout is very disruptive, basically it requires user changes. Like I said before, we don't want to be kind of having to roll this out and then roll back if we see an issue or something. So the idea is that by opting out like specific users that might see an issue, we can kind of quickly mitigate the issue and also allow the entire rollout to continue without waiting on those single users. Because essentially, like Shaquille mentioned, the kind of big benefit of this rollout in general is that we're removing the global limit and basically removing the the chances of the network contention between different users. So kind of like the earlier that we can get that rolled out, the better it is for the fleet as a whole. And yeah, so this basically just helps us de-risk the deployment and make sure that we're not blocked on like a small set of users needing to make invasive changes into their application. Now I'll hand it back to Shaquille.
Okay, so as I was telling before, since we are like changing some fundamental like accounting of the TCP memory, we are gonna like so here I'm showing you we actually exposed or like caused 2 bugs, kernel bugs. I'm gonna explain those how those happened. So first one was the like some particular workload started seeing unwarranted memcg ohms. Now, since we are charging for TCP memory, like normally we can say, okay, this is like, oh, you need more memory, just increase the limit. But on further inspection, what we find out that this job, the memcg usage, and like it was running like when we saw this job running on a single machine alone, and it hit the like very high memcg usage. And on closer inspection of the ohm report, we saw, okay, the memcg usage is high, but the free memory on the system is very high as well. So the actually like this memcg usage does not really correspond to its physical memory usage by this job. And what we found out was this was actually, as I said before, the caching, like very old Linux kernel caching for the TCP, so which is like 2 decades old. So kernel, as I said, like there is one counter, usage counter for the TCP memory, and kernel implements like per socket pre-charged cache. So each socket has its own cache in front of this single global counter. Whenever this socket needs memory, if it has enough memory in its local cache, good. Otherwise, it will go to the like global counter. It increment this more than what it needs, and then add the remaining into its local counter. On the free case, it will credit the free into its local until to a limit. And this limit can be, what we find out, can be 1 MB. So there were like situation, there were code paths where yeah, this local per socket cache can go up to 1 MB, and the application has like tens of thousands or even more, hundreds of thousands of sockets. You can clearly see like if majority of those sockets have this pre-cache, which is just a cache and does not really correspond to physical memory. We are just like causing this job to see the memcg ohms without actually using the memory. So the fix was to like move from per socket to the per CPU cache, and Eric fixed this. It's a recent change, I think 1 kernel back, I would say. So with this new change, the amount of cache, so previously it was the number of sockets into what the max, which is like 1 MB. With this, it was number of CPU, which is again, it's a, even at the highest, it will be like order of 100 into 1 MB. So that's the patch rates if you want to know more. However, like once this thing went in, we started getting reports of the like performance regression. memcg charging, previously like every socket was having its own cache, which was working fine. Now with this, with per CPU, memcg charging becomes the bottleneck. And I think kernel LKP performance, I think they sent out the email for performance regressions. So they reported that, oh, with this, we are seeing with these patch series, we are seeing 60-70% regression. So to fix that, we just like I just posted, I think a couple of weeks back. Now we have to I think MEMCG charging was getting free lunch. Now we have to actually improve and make the charging more performance critical. So there was the initial set of patches are posted, and I do plan to have more fixes follow up on there. Basically, it was if you see there was 2-3 issues. Again, false cache sharing between different members of the struct MEMCG or page counter. If you have seen morning's talk from Arnaldo, he also mentioned the struct page counter struct. So exactly that, but now it's the next level. It was the usage, and there is another the limit. They were sharing the same cache line. And the MEMCG per CPU, it basically pre-charges 32 pages. So we increase that to 64. So optimization there, we'll see how that goes. The second issue what we saw was we started for some specific workloads, we started seeing hard lookups and crashing the machines. So at the high level, or when we go and debug it, so the application was very network intensive, and it was creating a lot of threads and putting all of them in equal weight. So since it's network intensive, it sometimes does go and hit the limit and get killed. So what we saw was whenever this job gets killed, it caused the hard lookup, and we had hard lookup on panic on hard lookup, so it crashed the machine. So what we see after analysis and crash time analysis, so all these threads, thousands of threads in the equal weight, are linked in a singly linked list, linked in the linked list related to the equal. And whenever this packet comes, it go and wake up one of those threads. And what it does is basically, okay, the logic is there. So the thread, the front of the linked list, this is the thread. I woke it up and remove it from the list. However, when the job gets sick-killed or killed, all of its threads basically gets their state changed. So all these wakers from the software, you had to go through the each thread, the whole linked list, to see which threads it can wake up. So that caused the hard lookup. And the fix was also debugging was harder. Fix was simple is to always remove them from the linked list. So, all right. Now let me go over the work in progress. So we talked about we removed the system level TCP mem. We start charging a job, but we still have a situation where the system level TCP pressure. So again, the disconnect between the system pressure and the TCP pressure. Now, one idea is how about, so this static TCP mem is the issue. How about we do it dynamically, change? So based on the mem tree from the proc mem info. So for example, if you have good, enough memory, keep it unlimited. But if you falls below some threshold, or 500 MB or 1 GB, depending on the system size and the network speed size, you set it to low to cause all those TCP pressure mechanisms to get triggered. So we are currently experimenting with this, but it has two issues. The first is mem-free the right metric? Because if you have a lot of cold reclaimable memory page cache, mem-free is not really a good mechanism. You can easily reclaim all those instead of throttling the applications. The second is this throttling. We are running multiple jobs of different priorities. If we enable use the TCP mem, it will start causing the same. It will any socket which will hit at that time, it will get throttled. So high priority jobs can get throttled. So the possible solution we are kind of thinking of is, so mem-free seems fine if you are like doing like proactive reclaim as well, or your threshold is somehow within, so kswapd is like the kernel background reclaimer. The issue with the kswapd is like it's just one thread on a big system. It might not be, like it has small watermarks, those buffers like from the min to the atomic reserves, so it might not be sufficient. So most probably user space is preferable, where we can do multiple threads. And the second is, it's like we definitely need multiple thresholds of the TCP throttling. So like, for example, free memory falls below some threshold, only throttle low priority jobs. If it like at the edge, you can then throttle more jobs. And like I think we haven't like brainstormed much on the implementation, but I think it can be done. BPF. The one challenge might be is how to do it in a performance critical way, because these couple of these code paths are like very hot. So that's the system. The second here is the memcg level. What about the job? How you define the memcg level TCP pressure? So currently there is a system VM pressure which is being used to define the memcg TCP pressure for both V1 and V2. However, it kind of assume, like what it does is, like when there's a reclaim happening in your workload, it sees, okay, the number of scan pages, reclaimed pages divided by scan pages. So the memory reclaimer go and scan all the reclaimable memory. So it assumes, oh, you have reclaimable memory, reclaimable user memory. However, what about these network intensive like workloads whose majority of memory is like network memory or the kernel memory or file system specific workloads, or workloads who just mlock their memory, right? They don't have reclaim memory, so it kind of fails there. So now here one option is, what about the PSI? The issue with the PSI is it's like it's oblivious to the source of the memory pressure. We want to like link with the memcg memory pressure, not with any unrelated like system level event. And also it's kind of hierarchical. If you have a job like some subgroup which is in suffering, you don't want to suffer its siblings. Right? Okay. But memcg v2 provides a throttling mechanism or throttling limit, memory.high. It is a throttling. However, the issue with this, it throttles the CPU of the threads. If the usage goes above there, it does not kill the job. It throttles the CPU, which can actually make the TCP pressure bad, because from the TCP perspective, it wants the CPU to consume all the memory. So TCP, like memory.high is good, like it doesn't trigger the reclaim and whatnot, but the CPU throttling mechanism might not be good. So the possible solution here, again, we are kind of brainstorming, is something similar to memory.high, because but without the CPU throttling. We'll see how that goes. Let me, I think I have, this is the last slide, and if you have questions later on, but let me conclude. So for the multi-tenant servers, static TCP mem is harmful. And just to repeat, like if you run these multi-tenant systems in your infra, or you're planning to migrate from V1 to V2, you will be facing all these challenges what we mentioned here. And the main takeaways from our experience in deploying the TCP memcg. So the first, changing something fundamental will break old assumptions and will expose you to new bugs. There definitely will be new bugs. Second, the capability to have more fine-grained opt-in, opt-out jobs gives you the power to be more aggressive in deploying. Not a single user can deploy, can delay all your deployment. And the third, I think we didn't focus or go into too much detail here, but investing in the technologies like the dynamic right sizing, load balancing actually helps a lot. So you don't have to worry about how much memory, you as well as the owners, how much memory they need more, because these mechanisms will take care of them until of course they have some high level limits, but you will know exactly when those hit and what you need to do exactly. Okay, that's it. And if there are any questions, you can.
Any consideration for treating pressure on allocating these packets for TCP as as a full queue, and so doing read or ECN to back pressure the sender?
Any allocation on TCP?
So you can't allocate, so you're ooming your C group, right? But instead, you're observing that you have pressure. So you want to, it's the same as a queue being full on a network device, is how it feels to me. And so a solution to that is to do random early drop or explicit congestion notification. So the senders send you less.
You're asking for just within one job or at the system level?
I guess if you do it randomly, then stochastically it'll be by flow. But yeah, inside your job, I think is the answer.
Inside the job, yes. So we do want, so again, since TCP memory is any other memory, preferably what the mechanism what we want is, yes, we can this pushback and the mechanisms, but before that, there might be already easily reclaimable memory, which should go away. And at the end, so as you said, ohm is there are we have many job owners who prefer getting ohm killed than to get slowed down. So there are jobs like that. So and there are other jobs owners who want no ohms getting throttled or pushed back and slow down. So we do want a flexibility there, but yeah.
Thank you.
Maybe I can comment on your idea. I think it's a good idea, but if you drop incoming packet, you augment the chance of having more packet in out of order queues, and so you add fuel to the fire. So you need to be very careful of what packet you drop.
I have a question. It's related to the previous question. When in your slides you mentioned that the mechanism like memory high makes it worse, but does it apply universally both for the receive and transmit path? Wouldn't it actually work for the transmit path if you slow down the senders?
Sorry, I didn't get you. Can you repeat that question?
Yeah. So you said that the mechanism like memory high is not effective, and it makes the situation even worse because you want to consume the data there. But does it apply both for the transmit and receive path, or would it actually help with the transmit path?
So the issue is with the transmit TX path. On the receive path, this memory high actually triggers the reclaim, the CPU throttling on the software IQ for the memory.high is kind of broken. It doesn't work. So on the receive side, that's fine. And we do trigger the asynchronous reclaim whenever we are software IQ, we go over the memory.high. So which kind of helps as well. But we don't really do any enforcement. So the actual memory.high enforcement happens on the process context.
Yeah, so it's not like, or I mean, when there's task sending the data, it can allocate the memory, but then the throttling applies when it's returning to user space. And so it could work that if it's the same process that is sending the data, so it will be this exact process that is then throttled. So this could work for the transmitters, no?
You're asking the throttling mechanisms?
Yeah, the throttling mechanism would slow down the transmitter.
If you take CPU away from the
Yeah.
transmitter, he's not going to fill the bucket.
Yes. So you're saying since memory.high only throttles the senders, it might be like the other, its throttling is fine in that scenario, if I understand you correctly.
Yes.
I have to think more, but I think this is similar to what the normal, like at the sender side, we can, thread can get throttled. So it's similar. So on the, it might be more for like, I think just the how the memory high is implemented, because on the receive side, it's not really enforcing or doing the throttling. So it might work out of the box.
Yeah, I think the receive side, I think that's worse there. I
Okay,
agree.
oh, thanks. Yeah, I have to think more, but I think, yes, you are correct.
Okay, thank you.
Question there.
Almost made it.
Yes.
To your point about PSI, so with PSI, you mentioned you can't tell whether the process in the C group is suffering because of the C group limit or because there's a global memory shortage. But I didn't quite follow why that's a problem. So if you have outside pressure, machine is overloaded, pushing on the C group, and it's causing it to drop its page cache, it's causing it to swap its anonymous pages, wouldn't you also want to react in terms of reducing its TCP memory at that point?
So yeah, so the global reclaim is one, but it also can get triggered for the like compaction or huge page, or depending on the different. So if we can, I would say, like, let's say PSI can tell us memcg or the global like situation, then yes, that can be used. But one thing, like, I don't have a clear answer, is, but will we, like, by reducing or by throttling the TCP traffic of this job will help reduce the PSI? So currently, again, let's say we able to differentiate, or like we have a different PSI for the memcg and the global pressure, then that thing getting reduced, like throttling this, then yes, that can help as well. Have to see exactly like how to define like the intensity, how the PSI values corresponds to the intensive of how much we do how much aggressive we have to be. So those we have to like figure out.
Yeah, definitely.
Any more questions? There is one here. The CPU throttling is caused by the sync. It is sync reclaim, but there is also schedule out like at most 2 seconds as well in the memory.high. Okay. Any more questions? Okay.
Thank you very much.
Thanks.
Hello, is it working? Okay. Hello, everyone. Welcome to the track here. We have two speakers. We have, I'm John Hubbard. I'm just doing the MC, so I'll mostly be invisible. But we have two speakers. Jonathan Zhang is going to start off and talk for 45 minutes on the CXL. He'll give an introduction, and then we'll have Dave Early continue at the 45-minute point. Now we have got 3 mics, one here, a couple there. They're controlled by our AV guy who's going to see who's holding what. So it's this the usual story. I think we have everything working, and so we'll just see. Okay,
yeah,
so,
thank you, John.
Yeah.
Yeah. So I'm Jonathan. This session I give the meta CXL journey and learnings. I have 20 plus slides, so I'll try to go through as quickly as I can. And if you have any questions, just ask any time. I don't think we will be able to flush all the questions in this session. This is merely to spark the conversation. And actually tomorrow afternoon, there's an MC on CXL specifically. All right, so the work is not possible without a village. So we have all those reviewers from different companies. Thanks for the work. So for the agenda, we will go through the CXL memory technology quickly because some of you may not have heard about CXL. And then I'll talk about the meta status and our plan. Then specifically goes down into the memory management and at scale device management. Then finally, we have discussions. Make it full screen. Yeah. So. This one? Oh, that one. Okay. I saw it. Thank you very much. That's great collaboration. I learned something. It's the first time I use BBB. Not bad. Okay, so if you go to this link, this is a public link. You can download the current spec. It's 3.0, like 1,500 pages. So CXL, all the CXL devices, they are CXL protocol are built on top of PCIe protocol. All of them has to implement CXL.io, but depends on your usage. There are 3 different types. One type, the typical usage is like for NIC card, that smart NIC, that it implements CXL.io. So you have cache coherency. You have cache inside the CXL card that it cache coherency with the system memory. Or you can have like GPU or dense computation for AI that you implement both CXL.cache and CXL.memory. That means the device has memory that the host can access, not just the device. The memory buffers implements just the CXL.main, and the usage could be bandwidth and capacity expansion, and also storage class memories. And on. Those are just examples. So this is a diagram from the CXL spec. It shows you that in parallel to the PCIe protocol, it has defined the CXL.cache protocol and the CXL.main protocol for link layer, transaction layer, and there's arbitration and max layer. The current status. So CXL 1.1 was released, I believe, is 2019, and then 2.0 is 2020. 3.0 was released last month. And this PDF has this white paper. So if you don't want to read 1,500 pages, read these 3 pages. The processor, the CXL root port. Right now, we have 1.1 will be product launched soon, in a few months, I guess, I hope. And CXL 2.0 support right now is being worked out. The silicon companies are working hard on it. And the CXL memory devices, the 2.0 support will be product launched soon. And this table shows the differences between those 3 protocols. how it evolves. So this is the basic configuration. You can see that the processor has processor attached DIMMs, and the CXL card has a CXL attached DIMMs. So now, as a kernel developer, you say, what do I see from the kernel viewpoint, right? You run NUMA control. You see that this is a dual socket system. So you have two NUMA nodes, 0 and 1, both have CPU and memory. And you have a node 2, which does not have CPU, but has memory. So it's a CPU-less memory, NUMA node. So why is the industry excited about CXL? Because it actually decouples the compute and the memory. Now it's not tightly coupled. So that frees a lot of things, changes quite some consumptions or assumptions. Like it increases the bandwidth and the capacity. And it gives you tiered memory hierarchy. If you look at the right bottom, this pyramid, you see that CXL memory actually fits in nicely a void area for the latency. It allows you to have media diversities. Your CXL memory could be any type of memory. So your processor attached memory and CXL memory could be different. And CXL memory, you can do anything you want. It provides flexible and fungible memory. So this gives you something very hot term called software-defined memory now. You can do hot plug. You can have several hosts put in the same memory space, and you can share memory dynamically as well. So there are a number of published use cases. So from Meta, from Microsoft, from Cast. So links are all there. So Meta's plan. So we finished the system level prototyping, including software and hardware. We met the latency and the power budget. And latency impact studied, and we posted the kernel patches. Thanks for our kernel team. And we worked through multiple generations of system configuration, multiple generations of devices and processors. And we are working on the at-scale management. So this is our initial target, right? We start from simple use cases where CXL memory is added as system memory. It's static configuration. And for the kernel OS, by collaborating with the CXL kernel and OS community, we did the memory management part, and together we are working on the device management part. So memory management, what's our goal? So CXL provides more bandwidth to you, but in the meantime, the latency is longer. So we want to minimize the performance impact to the workload despite the memory latency. But in the meantime, we don't want the kernel to have to know the prior knowledge of the application behavior. And we don't want to do in-depth application tuning. But the kernel is not equipped to meet this goal. The paging mechanism is latency intensive. So paging from the hot memory to the warm memory. NUMA balancing is not able to move the pages to the CXL node, CPU-less NUMA node. And when there's a memory pressure, it behaves not so good. So to really study the workload and also study the impact of our patch to understand our design, we developed a user space profiling tool that you don't need to change the kernel. And this gives you some examples of our data that we have a web, cache 1, cache 2 warehouse workload, and we find out the access patterns. And then we have this diagram shows up how we design this user space profiling tool. We will have it posted upstream. The details are in our paper. We developed a patch set on transparent page placement. Jana sitting there actually is the author. So our design is we focus on the migration for the lightweight reclamation. We demote the code pages from the processor attached memory to the CXL memory and promote vice versa. We decoupled the allocation and reclamation, and we also added bits to so that we can observe the behavior. The effectiveness is that we have two configurations. One configuration is all 96 gig of memory are attached to the processor. Another configuration is 64 gig attached to processor, and 32 gig is a CXL memory. In this case, we can find that with the TPP patch, the performance impact to the workload is less than 1%. So that's good enough for us in exchange for other benefits. Now, so what I said about that patch set is for latency intensive workload. Now, what about bandwidth intensive workload, right? What about the bandwidth is also at its bottleneck if it is a processor attached memory? So we have this interleave improvement that you can tune, you can manually define what's your interleave ratio, right? So if it is the default, the current corner default is 1-to-1 ratio. In this case, we see 40% drop. But if we change the ratio to 5-to-1, we get 8% increase in terms of performance. So CXL memory actually improves the workload because now you have data flow not just goes through the memory controller on the processor, it also goes through the PCIe subsystem, going into the cores. And we have an interesting finding is that the optimal ratio, it actually depends mostly on the hardware, the shape of the latency and the bandwidth curves. It does not have too much correlations with the workload itself, as long as the workload is bandwidth intensive. That's our observation. So any questions so far? Now we go to the at-scale management. So now, it all looks good if you work on a rack or single system, but what happens if you have a lot of things, a data center full of CXL device, how do you manage it? So for the memory to work, as long as the firmware works, right? It will just work automatically. The CXL memory is either added as system memory when the Linux boots up, start to boot up, or you can access it through spatial devices such as DAX device, direct access device. You can do either way. However, now the CXL device is actually a PCIe device. The memory is not managed by the core directly. So we need a CXL driver. The CXL driver can communicate with the device through mailbox. Mailbox is defined in the spec. And the driver can discover and enumerate the hierarchy. It can find out how many CXL root port I have down there, how many switches are there, each switch, how many devices are there. So find out all the hierarchies. And the CXL driver is also designed to a number of other things, like firmware upgrade, like event management, because CXL devices generate events, like hardware error event. Oh, I have a warning, I'm too hot, things like that. Now, there's a complication here, is that you have host, you have device. Host and device could support different CXL versions. So a clean case, you have a 2.0 host and 2.0 device. Now, as I said, we will have 1.1 host in the market soon. But all the device vendors actually will roll out devices. This is 2.0. Now, 2.0, you have two modes. One is called RCRB mode, another is called non-RCRB mode. So the CXL driver needs to support both of them so that the production system could be supported by the CXL driver. So that's something the kernel community is working on right now. For example, you can see that the register mappings are different, and also, the register mappings are different, and then RCRB is not exposed to the kernel at this moment. It's not config space access regular. Now, talk about event management. So the CXL device could speed out different types of events. Could be CXL memory error events, that's green, And you could have the red one, the other spec defined events, like say, oh, I generated some performance data you can grab, or device vendor specific events. And this is a design that's currently on the paper. There's no code for it. So I hope to work with the industry to really get this done together and refine it. And then it goes through the kernel. You have the CXL driver does pooling, does interrupt, does the command handling, and does the event handling framework. And then the data flows to the trace buffer. Then all the agent, including the user space, could register for it and get new events. And once with the new events, it needs to go through the dispatcher. Some of the data, the green data, the RAS data goes to the RAS daemon. So that from user's viewpoint, all the dim errors, right? Processor dim error or the CXL dim error, they all go through RAS daemon, show up there nicely. You just say, oh, this memory attached to this processor memory controller had an error. That memory is a CXL memory, is represented by this PCIe BDF, right? Boss device function had an error. So, and then flows to the device vendor's specific event handler. So we are thinking this design so that device vendor could add their extensions, and the customer, like us, like Meta, we could have our own handlers to suit for our formats and policy needs. So this is on the paper. We hope to work with the industry to get it improved. Another complication brought forth by CXL is a reset. So PCIe, we all know that for PCIe device, there is hard reset, warm reset, and cold reset. So that's cool. That's almost the same for CXL. Now, there is added something called a CXL reset. So CXL reset means when resets, it resets the entire CXL.io and CXL.main protocol for all layers. Now, the complication is, right, for the entire device. Now, the complication is you might have multiple hosts sharing a device. This does not exist today, but it exists on the paper. And the device vendors and silicon vendors will get it, make it happen. Now it's up to kernel community to deal with it. HDM region. So HDM is a term you might not be familiar with. This is a CXL spec defined term. It's called host managed device memory. So in the device, you could have some memory just managed by the device, like today's GPU device, for example. And you could have some of the memory is actually CXL memory that host can access, issue load store command directly to access them. So that region might migrate from one host to another host, right? So when you do reset, you need to consider this. And that's from the device viewpoint. Now from the host side, the host, you have a piece of memory region. The piece of memory region now points to one CXL device, next time may point to another CXL device. So those are the things needs to be considered. Now, the reset management, the CXL driver flow to support the reset. Before the reset, you need to offline the HDM ranges and make sure the host stop initiating any new requests and clear randomize the content from the security viewpoint. Because if you don't be careful, your memory now is exposed to another host or to another application. Then you issue the CXL, you tell the device to do a CXL reset. And after that, reinitialize all the CXL functions and reinitialize the HDM ranges. Switching to another topic is that today, how do you know as a customer, as a user, how do you know the information about the processor attached memory? You run DMID code. Now, the problem with the current DMID code is that it only shows you the processor attached memory data. Today, if you connect a CXL device, you don't see the memory from the CXL device. So if your firmware supports it, then it would work, right? So get it to work or add it. We basically have CXL, have host firmware in Linux, by the way. Now, DMI code is filled in by the firmware, right? So that's a static information. But going forward, actually the hot memory plug becomes common, especially with CXL memory, because now it's just a PCIe card. And also you can switch between different hosts with a CXL switch. Then you actually don't need to do anything physical to plug and unplug memory. And the DMI decode only shows the system memory, does not show memories accessible through devices. Well, here, devices means Linux devices. This is DAX devices. So the proposal. What about something like LSMIM? It's similar to LSPCI, but it's actually more complicated than LSPCI. I'm not going through LSPCI today because there are patches posted for LSPCI, because LSPCI today only understands PCIe language, does not understand the CXL dialect. So there's patch set for that already. Now, the memory side, if we focus on the memory side, how to show the kernel data, how to show the memory media information, how to show the interleave information. You could interleave between the CXL devices or interleave between CXL and the processor memories. That's all possible. And the memory segment information, what memory segment right now is provided by system memory, what are represented accessible through the kernel memory devices. And what's the CXL hierarchies, right? With today's CXL memory, CXL driver, kudos to the CXL driver community. In the CCFS, the hierarchy is there. We just need to show to the user nicely. Okay. Pretty quick, 20 minutes. So call to action. So yeah, there are a lot of things going on. If you go to the Linux-CXL mailing list, you see all the work about the at-scale management. Now, if you existing memory mailing list, memory management, they have a lot of discussions. Yesterday, there was a session, BOF session from Google. Yeah, so and also join the CXL forum. And there's a system software work group and a memory system work group. Tomorrow, 3 to 6:30 in Herbert over there, our Samsung friends and the Intel friends will lead the CXL macro conference. Yeah, it's only 3.5 hours, but next year it could be like 8 hours. Grab your coffee. So yeah, kernel memory. So here are some. So even though our patch set meets our kernel needs, right? But we think that in longer term, something needs to be done. Especially from the tuning point of view. So for interleaving, right? I said that we have to run some experiments to find the best interleave ratio. So how to tune the interleave ratio with less tuning effort. Second, the latency sensitive workload and the bandwidth sensitive workload. Right now, we improve their performance by different methods. Now, they are exclusive technologies. On one device, you might have both workloads running. What do you do? For us, today is not a problem, but for the industry, right? Tiered memory hierarchy. This kernel community has been discussing this for some years. We need some solutions. It will get more and more complicated. In our case, we have only two configurations. One is a processor attached memory, and one is CXL memory. In the future, you have a lot more. You could have a lot more. Like with switches, you add the latencies, some latencies, right? And you could have different memory, CXL memory media that have different have different memory latency characteristics. So, and today's memory hierarchy, memory management does not really consider the actual latency and bandwidth. It does not really consider that. It's not smart enough. Hot plug, yeah. That hot plug will be the foundation for the software-defined memory. So today we have nothing for that. Hot plug, you need to consider the traffic management, device management, memory management, security. It's a lot of things needs to be figured out. Memory sharing. Once you have memory sharing, how to maximize its impact? Now you don't need to move data from one host to another host. How to use that? It looks very appealing, but how to use that? How to benchmark it? Any questions from the audience?
Hey, I just have a question. What are, I guess, the limitations of you have the switches, like the distances that you can have this CXL shared memory between two hosts? Like, if you can talk about that.
Yeah, I'm not sure I heard clearly about your question.
What are the limitations of distance? You know that.
Yeah. So if we go back here. This is a theoretical data. Looks very nice on the paper, right? On the actual system, we did achieve this, but it's a direct connection from the host to the device, right? Now, if you add switch in between, switch will add latency. How much? We don't know, right? Switch will add latency. And so this number, 170 to 250 nanoseconds, is about the same as if you're accessing the memory across the processor. So processor 1's core, processor 0's core access processor 1's memory, about the same. Yeah.
We've got Conan Kudo raising his hand on the chat.
Yeah. Did I answer your question?
Yeah.
Yeah, we can talk more. What's the question?
Yeah. Conan, go ahead.
I am not able to see it.
Yeah,
would
maybe
you
just go ahead and type your question in there. I'll catch it when it shows up in the chat. So let's continue.
Sorry, I didn't hear. Can you please repeat?
Someone raised their hand in the chat, but we're not able to hear them talking.
Okay.
So I'll just wait till they.
Yeah, we need to wait a bit until he taps in. Any other questions on the memory?
Here. Sorry, me again. So let's say that you were running virtualized loads. The expected level of steal is pretty much, you're anticipating the expected level of steal on like virtual VMs to be about the same as if this was just a regular NUMA node with, you know, a CPU and memory attached.
Yeah, it should be the same. If I understand your question correctly, it is the same because now it's just a piece of memory that anybody, including VMs, can access it freely. You just need to be able. You just need to keep in mind that now, in terms of zeroing the memory, you switch from VM to another VM. In terms of zeroing, you need to be more careful. Yeah. The processor attached memory might host firmware already set it up, but now device is different. You may just have to tell the device to zero the memory. or randomize it. Yeah.
My question is similar to him. So from a user space perspective, you just load and store into a memory position and it goes to CXL memory?
Yeah.
Or do you need to have like a page fault to access CXL? So for instance, there is a TLB entry for the CXL memory, so you can convert from virtual to physical. Is this similar to a regular memory, or is it a different path?
It's the same path. So if the host firmware is configured to add the CXL memory as system memory, you just access it, load and store. It's no difference at all. No difference at all. If it is added as DAX device memory, then you need to bind it to it.
Thank you.
Yeah, so that if you are CXL memory aware application, you can do that way. Any other question?
Sorry, me again. The actual memory on the back end, is there any way to, I guess what I'm trying to ask is the memory in any way virtualized? So for example, you had a failure and you could replace in runtime your backend memory, and whatever P2Vs would just be remapped.
Today it doesn't. Today it is not. So this is a stability problem that needs to be managed very well. Is that today you know that if system memory has uncorrectable error, and it happened in the kernel critical region, then the kernel simply cannot run. If it's not critical region, you can do a lot of things just to quarantine it. Now, CXL memory is in the same category as system memory now. So today, if some error happened on PCIe device, so what? Linux kernel is still happy, even though the apps is not happy, VM is not happy, but the kernel is happy. This is that this with CXL device, if there's a device error or CXL memory error, it impacts the kernel, has the potential. So the stability it becomes very important. The device vendor needs to do a good job.
Yeah, and a follow-up question. The backing devices, are they dynamic add at runtime, or is this something that has to be, after post?
It is dynamic in terms of how you map the memories. You can change it at runtime. However, you cannot dynamically provision a device. You cannot say, let's say 2 hosts connect to a switch to the same device. You have to at this moment, you have to shut down both server and then you do the switch through the firmware. Kernel is not able to do that today.
Okay.
Yeah.
Thank you. That was the last one.
Yeah. Good questions. Hope in a few years the answer is different. Yeah. Okay. Okay. Yeah. You have a question? Online?
Just a bit of a follow-on from that. Would you envision it becoming ourselves that where you would not want the kernel to run with the CXL device and just have these CXL devices used for like user space allocations, and you would keep the kernel in DRAM?
You could configure the kernel in a way that critical regions just go through the processor attached memory. You could do that. Yeah. Now the impact to the application, right, is still there for the VMs. Yeah. Yeah, that's a good point. So if not, we go to the last page. Oh, I'm too fast. Performance tuning tools. Could some of the memory performance tuning be done in user space? How to change the latency and the bandwidth profile of CXL memory regions to simulate memory hierarchy. This is basically about how to make the kernel developers' job easier. You don't want to have Meta has the luxury of having the devices. We have racks and racks of CXL devices we can work with. But memory management developers, how do they simulate that? how to change the behavior of the benchmarking apps, such as the page type ratio, memory access pattern, to simulate workloads. Right. So those are all about the tools of helping memory management work, of simulating the device characteristics, the system device characteristics, and workload characteristics. How to do that? So we don't have answer. Some of you are smarter and will have answers. We look forward to that. Any questions on this? Actually, there's the last page. Or any other questions on any other aspects regarding CXL?
Okay. Pankaj Gupta asks, does CXL DAX device backend, is it different from the traditional NVDIM device DAX backend?
So the question is about NVDIM.
So let me try it again. Is the CXL DAX device backend different than the traditional NVDIM?
Oh, I see. So the question is the CXL DAX device backend the same as the backend for NVDIM? It is not exactly the same, but they are built upon the NVDIM device driver. So instead of it's a payment device, right now it's called HMAN device. I forgot the term. So if you go to the driver Linux kernel code, you see driver payment, and then you have a payment directory and you have a HMAN directory. So they share some infrastructure, but a different device driver. Yeah. So the DAX device, but you can use DAX control command, right, to change the CXL memory from system memory to back to the DAX controlled memory, or vice versa. Yeah, that's all working today. Any other questions? Thank you.
Things. Okay, so you wanted to simulate things. For simulation, you can use 2-socket, and there's a way to change the bandwidth between 2 sockets, so it's CPU dependent, AMD, Intel, and whatnot. I don't know if it's public, but they can do it.
Yeah. Let's discuss more. A lot of work to be done here. It's exciting. Okay, cool. That's the section. Yeah.
Oh, sorry, I forgot. I totally forgot. Don't. It's all live streamed, so you can just cut it up. I totally forgot. Sorry, I was watching the other thing. There's one on they're beside John on the chair, I think. At least two of them, I think. All right, we're probably ready to go. All right, guys. Good morning, everyone, or evening. Sorry, in the wrong time zone. I'm here to talk about the Nouveau project in the times of firmware. Just for those, I'm David Early. I'm a distinguished engineer. I work in Red Hat in Australia. Don't let the accent confuse you. I'm from here, but live there. I'm also the upstream kernel maintainer for all of graphics and a bunch of user space stuff and a few other projects. Nouveau, I don't work on that much anymore, but I'm going to give this topic because it's topical and I have been working on it lately. So I will start by just giving a little bit of hardware history from the NVIDIA side. This is more of a very sketchy summary. It's not entirely accurate. It's just quickly cobbled together from Wikipedia. So, but it gives you just an idea of how far back NVIDIA hardware stretches. It probably goes back a bit further, but how far back we've cared to write for this. You can pretty much ignore the first two lines. We've decided that that's too old to care about, but it started getting interesting really about 2006, the NV50. The big change was the introduction of this per context virtual memory addresses. You'll see what that's important, but that's a major sort of turning point for graphics that this started getting introduced. And then they kept progressing. You can see it's pretty much at every 2-year progression as they went on. You see the highlights of Kepler was where Vulkan got supported. Maxwell came in 2 parts. There was Maxwell and Maxwell 2, which were pretty much the same, but they had some changes. And one of the ones was when a thing called signed firmware started. And then we progressed up through things. We got Pascal, Volta, Turing, and Ampere. And then highlighted for Turing is a thing called GSP support. I'll get to what that is and why it's important. So with Maxwell 2, this thing called signed firmware started to happen. And for secure boot reasons and other reasons, it was decided that you shouldn't be allowed to just write your own firmware for these devices. You need to get firmware that has been signed by NVIDIA and load it into a number of little processors on the device. This complicated stuff for the Nouveau project, and I'll get into that a bit further, but the sort of compromise position we had reached with NVIDIA over the last few years has been that they would provide us with signed firmware blobs that we would then poke into the GPU using Nouveau in various places. And there could be 2 of these, 5 of these. There was a number of them. And the sequence of ordering was very complicated. It's very hard to get right, unstable. Yeah, it's been very painful for the last few years to make Nouveau go anywhere. And even when you've done that, all you succeeded in doing was turning the device on. You can't make it reclock. You can't make it go faster. Most devices get booted up at the slowest possible clock speeds because they just want to keep them the power off. So pretty much when this started happening, this is when Nouveau sort of, well, we can't make it go fast. What's the investment? What's the future? It's like it became a bit of a big problem. And I'll get into what we have to deal with later. But this is sort of a watershed line I want to identify early. But then recently, around the Turing time, introduced with the NVIDIA R515 driver, there's a thing called GSP firmware. And this is a new development that NVIDIA rolled out. It's only Turing and above. And what they've done is they've put a processor, which is a RISC-V based processor, onto the GPU. Now, the GPU already has maybe 6 or 7 little microprocessors on it. That's what we're putting up the firmware for. This is kind of like the one to rule them all firm with GSP, RISC-V. The firmware file for this is in the range of 30 megabytes, 40 megabytes. It's not, most of our firmwares up to now have been in the 256K is enough for any one type of space, but this is in the 30 megabytes is a lot of firmware. But it requires this GSP processor to be there. What NVIDIA have done is taken their driver got out of scissors, worked our way up through it, put all this part into the firmware, made a nice RPC API between them, and then firmware, kernel, user space. So they've cut it up and added another little abstraction layer in the middle. That sort of was announced at the same time as this project, which was that NVIDIA were going to provide an open source kernel module. This is a fork of their proprietary driver using the firmware, where everything was in the firmware. And when they did that, it's like, oh, this layer between the firmware and the user space, it's in the kernel. It's not really secret anymore. There's nothing we care about to really have to keep closed source anymore. So, well, we can actually we have use cases where people have wanted an open source driver for that place. We can solve them. This was produced. So we've achieved at least the base level of an open source kernel driver for the when you have the GSP firmware. So the last two. Unfortunately, this due to it being a fork and a split of their current proprietary driver, it's not really what we would call upstream kernel code. It's not like in any way look or act like what any of the graphics drivers or drivers that we have in the tree. So in terms of what can we do with it, I'll get into it later, but it's like we ain't taking that and sticking it into the kernel. So. And that's kind of the state of play of where we are now with the on the NVIDIA hardware side, on the firmware side. And that leads me into the Nouveau project. Where did that come from and why does that exist? So Nouveau was started in 2007, maybe a bit earlier, a bit later. It was at that stage that we should do reverse engineer NVIDIA GPUs and write a driver for them ourselves because, you know, we didn't see it as a possibility to get something. So it has support in the kernel and user space from NV04 pretty much up to Ampere in various states of disrepair. Some device, I think we got acceleration on to Turing, but sometimes Turing just doesn't boot because the firmware doesn't work, and sometimes we have I think we've recently got, I think Ampere support is there. Again, some devices just don't boot because the firmware doesn't boot. But we pretty much have like the minimal acceptable driver to either get the operating system to boot, switch off the NVIDIA card so your laptop battery doesn't die, or let you install the NVIDIA binary driver so you can do stuff and have your laptop battery die. Choices are, either way, your laptop battery is probably not going to be the best thing. But this project, it's stagnated a bit recently. There's a lot of reasons. It's not just a simple, oh, you know, it hasn't been. So one big problem we have with a community-backed open source driver is when somebody gets good and gets well known in the community, people start offering them jobs, just the way it is. But nobody really offers you a job to work on Nouveau because there's no real, like everyone just, you know, NVIDIA is probably, and Red Hat are probably the only two companies that could even think about doing this. And NVIDIA really haven't, and Red Hat hasn't got enough, you know, we don't have enough engineering requirements to support multiple engineers working on this. So it was a bit of a problem. Anytime we've attracted developer attention, they invariably leave and start working on graphics drivers for a company that will pay them because you would. Getting paid is important. So it's left us in a bit of a place where we've only really had one full-time developer on this, who's Ben Skeggs, who works at Red Hat. But once this signed firmware thing happened and no power management happened, it got a bit disheartening, I suppose is the word, because you don't ever see a future where you could compete with the real driver. Like one of the better moments in my career has been writing the driver, the RAD-V driver for AMD and beating the AMD stack with an open source driver. Because, you know, we've always said we could do it, but no one's ever gotten to the point. And then when we did, we've done it a couple of times now maybe, but we could never achieve that with NVIDIA hardware. It's just, what was the point of putting all that effort into writing all these things if you were never going to get the reclocking working? So, you know, there's a lot of like, oh, well, no point putting in too much effort. And then while that was sort of going on, Ben was currently also in the firmware loading hell of, can we get these firmwares to load? No, reverse engineer, go to NVIDIA, reverse engineer, go back to NVIDIA, cycle that just went around and around. And he wasted a lot of time trying to get firmwares to boot. So Yeah, it sort of has had a little break, stagnant. So I'll just go through sort of a little status of where things are when it sort of has stagnated. So the kernel driver is, Nouveau driver in the kernel. It's been mostly a hardware enablement activity lately. It's mostly been trying to add support for Turing, trying to add support for Ampere, trying to get the firmwares NVIDIA give you, booting on it. The NVIDIA firmwares that they give you aren't the same firmwares they use on their driver, so they don't test them as much. And then so it's a constant work on that. The secure boot stuff has really complicated life. It's made it very difficult to do anything. There's a lot of stuff that only NVIDIA can really debug. But recently, with all of this new firmware plans that they had, we decided, well, look, this firmware will allow us to do all of this stuff. It's a very high-level interface. We can write a driver to it. So we've actually started writing the GSP support into the kernel driver. That's the one project that's going on at the moment in that area. So we're sort of hoping to at least be able to prove that we can use the NVIDIA firmware to do display and to do command submission and reclock stuff. So we will see. It has an OpenGL driver in Mesa. In theory, I think it has passed OpenGL 4.5 conformance on someone's laptop, but no one has ever submitted it for actual conformance. We've had horribly broken multi-threading context support. So if you were running if you're running standard single-threaded like old games, it might work, but anything modern like Firefoxes or just modern games would get very confused and it would fall over. But that's actually recently been fixed, thankfully. But again, it got to a point, the reclocking thing happened, and everyone's like, well, there's no point writing a highly up or better optimized compiler if I can't reclock the card. There's no value in it for me. I'm not, it's not going to be a fun exercise. So again, it's kind of stalled out at that point where it kind of works. It's enough to run your GNOME shell desktop compositor, but anything else, it's not really great. But part of this reboot is, well, there's an obvious gap. We don't have a Vulkan driver at all. There's been we have a Vulkan driver for Intro, we have a Vulkan driver for AMD and Mesa, but we've never had a Vulkan driver for Nouveau. So some sort of news that we did recently is we have started a Vulkan driver, or Jason here has mostly started a Vulkan driver with help from myself and one other Carol at Red Hat. So we started just implementing a Vulkan driver for Vulkan Mobile for Kepler to Ampere. Currently it's passing, is that correct number? 85? Less? 92% of the CTS for 1.0. However, it requires, we've probably going to get it as far as we can in user space, but to actually make it what we want, we're going to have to bring the kernel up to meet it. So we started it, got a kernel we're trying to get the firmware working on, and we got them that way, and then we got the user space and we're getting the Vulkan driver, but this bit's kind of missing. So we're going to require this new user space APIs to finish it off. So what sort of problems do we have in our user space APIs? I don't know if anyone's aware with some of the kernel. We've got these old kernel for AMD hardware called Radeon, and we've got a new one called AMD GPU. And Radeon is probably the same level as where Nouveau stopped. And we never continued on to get all the features that the AMD GPU driver has. But the three features we really need to get Vulkan going are these, and I'll go through them. So the first one is you need to split the buffer objects, so the memory allocations from the physical memory allocations from the virtual memory allocations. Currently, when you allocate a buffer with Nouveau, you say, I want this much memory space. You give it a bunch of flags about what the memory space should look like, tilings and all these things. And it allocates the physical memory and puts it into the virtual memory space for the process you're running on the GPU side, GPU's virtual memory space. That's fine for OpenGL, but it doesn't work for Vulkan. You need to have that done in two steps. You need to be allocating the physical memory in one step, and then you have to attach ranges or pieces of that physical memory allocation into the virtual memory address space with all these flags set. And splitting that API is pretty much a fundamental thing we have to do to get proper Vulkan support. So that's sort of step one. The second thing is we need a thing called sync objects. So there's these synchronization objects where when you submit work to the GPU, you pass in an array of objects to wait on, the work to do, and an array of objects to signal. And when you do multiple submissions, you can have those work off each other. So the scheduler in the kernel can go, oh, this one needs to wait on this stuff. I won't send it to the hardware till I see that signal. And it's how you do proper interleaving. Now, in theory, we could get away without this, but I think Jason has said he does not want to do hackarounds for this. So we're going to have to get some sort of synchronization object handling done. And both of these kind of lead to the final change, which is, well, if we're doing these things, we may as well try and bring ourselves up to what was considered a modern virtual memory management and execution API that supports what Vulkan needs. In our community, that's been called a thing called VM bind. We've been looking at it for the Intel driver. AMD GPU has a lot of the pieces of it. I think there's been another couple of drivers that are interested in doing it. So it's like it's an API for managing the virtual memory's address space and command submission, but also doing them on a sort of a timeline. So you can sort of say, here's a bunch of execution, and when that's finished, here's a bunch of virtual memory changes, and when that's finished, here's more execution, and you can interleave things, and the Vulkan API has support for that through a thing called sparse. So these are what I would say non-trivial projects. They're quite large, and they are probably going to be sort of blocker to move forward with Nuvo and the users and the Vulkan driver. So when we get the reclocking bits in place, these are the sort of priorities we have to hit. We've started looking into them, but there's a good bit of work, and they're kind of interleaved. Every time I start looking into this, I get into one of those, oh, this bit needs that bit, needs that bit, and you keep going around in circles, going back to where you started. It's like, how do we figure out where to start and how to do it incrementally? It's one of these. If you implemented all these 3 APIs and dropped them on the mailing list, you'd be, I don't know, probably a few thousand lines or maybe 10, 20,000 lines. It'd be a lot of code to review, a lot of patches. How do we do that incrementally? How do we put it into the kernel slowly? How do we get a starting point? So there's a bit of management work about how we can actually upstream it even as we do it. So also there's a few upcoming problems that we haven't really faced yet. One is the firmware size. So 30 meg firmware is kind of big. We like to stick the firmwares into the init RAM FS. You might have 3 or 4 different init RAM FSs. And people always go, oh, my boot runs out of space. Well, this is going to exasperate your /boot running out of space. It's a problem. It's like, I'm not sure how much of a problem it's going to be, but it's exasperated even more by the fact that currently the NVIDIA firmwares that we're getting don't have any stable firmware ABI. So they version lock their whole stack. Their firmware, their open driver kernel module, their user space, it's all version locked. It all only works if everything's in the same number, which is great for them, not so good for us. So the problem comes if we go, okay, here on their 515 version driver, we start on that. But then they fix something in their 540 that we need, or they add a hardware support. Now we have to ship the 515 and the 540. And then on 580, they had something new and more hardware support. We have to ship the 15, the 40, and the 80. Like, we would not want to ship every single one they released because that would really, but we're going to have to monitor what's a bug fix, what's needed, what's going. So there's a lot of overhead on what happens. And as we stack up the ones that we decide to support in the upstream kernel, those ones have to continuously be shipped. I'm trying to think of ways that we can work around this, like by maybe just waiting till we're on the root partition before we load the graphics driver, and doing stuff. Could we have not in the old days that would have been a pain because we would have had VGA, but UEFI, it mightn't be as bad a problem that we can actually just delay loading and not stick these in the init RAM FS at all. I will see. I haven't fully thought out the consequences of this yet, but it may be an option. So far, we've only had. We're only been looking at the R515 release driver, so there's been a couple of bug fixes to that firmware, but yeah, we have not got a good plan on how to deal with this long term because it's going to get messy. Of course, yeah, we will be discussing it with NVIDIA over time and seeing what can change, but at this stage, that's where we're at. And then, kind of more, what other sort of plans and possibilities does this enable? Well, putting this into Nouveau, it's sort of like hammering in the NVIDIA firmware API into a driver that has its own idea of how all the things work and all its own layering. Like, it may make sense not to do that. It may make sense to just stand up a brand new driver that just does that with the user API of Nouveau or something, the new user API on top of it. It may be a smaller, maintainability, and it lets you forget about the old stuff. Lets you not forget about it, but it lets you, it's in a different driver. It's not going to get disturbed by this going forward, and we just concentrate on this path for choring forever.
There's a question from online from Conan Kudo. Says maybe simple DRM to Novia handoff would fix that firmware problem.
Yeah, the question is whether we can use simple DRM to do the handoff. Yeah, that's one of the other things that kind of let us maybe just skip loading the driver till later. That we've changed things so that we don't have a frame buffer driver. We've got the simple DRM driver, and we could do graphical stuff and Wayland stuff and things without having brought up the NVIDIA drivers, the Nouveau driver loaded. So yeah, it helps that problem, but it's not just a simple solution. So yeah, that's kind of up in the air whether there's we could do something with a GSP only driver. Also the idea of now that we're able to accelerate, now we can actually reclock the firmware and do stuff. Can we build something that can do compute properly? Can we build like a stack that's actually cross-vendor and not proprietary, like something that's, if you look at the compute scene at the moment, there's CUDA, there's ROCm from AMD, there's one API from Intel. It's all vendor. There's no cooperation. There's no community. There's nothing around it. It's pretty much everyone just cares about themselves. Can we fix that? Like, now that we have the ability to actually run something on all the 3 GPU vendors, can we fix that? Can we get something that's useful in the ARM space? Can we get something that's common code? What we've done with the kernel, can we do that in user space more? It's a big open question. We've done it for Vulkan. We've done it for OpenGL. I don't see why we can't do it, but it's going to take a lot of time and probably a lot of money. I think that's all I got. Yeah. So if there's any questions, I don't think I've forgotten anything. But
I have a questions.
Oh, online?
Yeah.
Where is it? Online.
Yeah. Online. Yeah. Yeah. Regards to the compute stack, and so far there is many compute stack in the community, such as the AMD have ROCm's compute stack, and Intel have Leo compute stack as well. Do you have any plan to develop a unified compute stack, such as the DRM graphics, for the general GPU portion? Yeah.
I didn't quite get all of that, but I think the question was about creating like a general compute stack. I can get the start of it.
Yeah. Yes. Right.
Yeah. Well, the plan is that we should be able to come up with some sort of compute stack that's based on DRM, does everything the same as the graphics stack, same as we've done with Mesa. We lack an API to do it too so far, but OpenCL kind of is the API, but it may not be the one we want. There's a bit of work there to be done. But I think this opens the possibility of doing that. I hope that answered the question. If not, type it in and I can hear it.
Okay, I see. So,
yeah, I'll just get it on the mic.
I know we're supposed to talk.
Hey, so isn't there something like a Vulkan compute as well?
Yeah, so the question is Vulkan compute stack. Is Vulkan compute's a thing? It is, but it's only really more for your sort of app desktop-y game type situation. It's not really a compute stack that's going to do what CUDA can do or can do. It's more of the replacement for OpenGL. It's gotten better than OpenGL compute by a long way, but it's not gotten all the way there yet. I think Jason.
Yeah, so there is desire within Kronos and other places to make Vulkan something that you can use for what you might call more serious compute or scientific compute, but it's never going to become the full software stack that like CUDA is today. So CUDA, you've got single source and you've got all this compiler stuff that happens and all these tools. Vulkan at the most would ever only be like the runtime underneath, and there's still a whole software stack to build on top of it. So while the runtime may eventually get capable of that, it's never going to be the whole thing. There's always going to have to be something else.
Any other questions?
I also wanted to ask about the initramfs and firmware bundling. So I suspect that not all systems initialize the frame buffer on the newer GPUs in BIOS or FE. So you would always have to bundle that firmware into the initramfs, right? Like on ARM systems.
Sorry, I missed a bit in the middle.
I mean, like on x86, the GPU, I believe, is initialized by BIOS, and you get simple DRM out of it, right? But on ARM systems, you always have to bundle the firmware into the initramfs because the GPU is not initialized by anything.
Yeah, so that's the question is that, yeah, so the x86, you got your BIOS at UEFI, it's the frame buffer device for you, but on a lot of ARM systems, you don't have anything till the graphics driver loads. There is nothing setting up some of the devices, especially more on the embedded side. I think on the bigger side, it's not so bad. But yeah, I think at that point we're going to have to, see what we can do, because again, they're going to have the same problem. Maybe we should. Yeah, that's when you get into, can U-boot do something, or is there some way we can? But there's probably not much. In the old days, what used to happen was someone would stick an x86 emulator into your U-boot and boot it that way. But
so with U-boot, there is FE implementation now, so it might be possible to start some sort of an FE binary which would initialize the GPU, possibly, maybe. They did something like that with network cards already to boot from iSCSI, so maybe.
And I don't know what would happen if somebody, crazy person, decides to take the NVIDIA GSP firmware and load it at U-boot time, bring up the card there, and then boots the operating system and tries to reinstall a newer version of the GPU firmware on it while it's running. I would suggest someone should try that at home and not near me. Kind of, I suppose. Yeah, the BIOS I don't think has quite that much functionality in it.
I was just saying, this is probably what the driver does already today. I mean, the UEFI option ROM in the card is probably already loading something in there. Yeah. That being said, I mean, we went down that path for other things in the past. And yes, the firmware were smaller, but they were still big for the time. And the end result is often, do we really need to have a frame buffer at that point? Can we boot more quickly and then have user space on the final system, bring the rest of the thing up?
Yeah, no, with the NVIDIA stuff, you can't do anything to develop the firmware.
Well, exactly. My point is, the initramfs might not be the right way to do that.
Yeah.
And have a small initramfs boot quicker to the real root, and then get your firmware.
I was just sitting in the session after Leonard's yesterday at systemd and talking about reworking the RD system, and the presenter from Red Hat there, with quite a straight face, suggested that they should put the entire sound stack and the entire graphics stack inside the init.rd so that it was available to debug possible boot problems.
You might remember my strong disagreement with this approach. Not yet.
Robert?
Excuse me, can you forward this?
Well, I mean, since I've been called out, I would say that, I mean, we're talking about a few times, maybe 30 megabytes, right? So it sounds like if you have multiple kernels and you want to support multiple cards, you need, well, let's say a storage of 300 megabytes, 500 megabytes. If you are smart about this, you can load just one of those firmwares from the specific boot. And I think this is entirely doable, right? I mean,
Yeah, and I brought that up recently on Fedora Bailey List about whether we could actually just package the firmwares into a separate init RAMFS or something like that, so that we don't have to have 3 of them for every kernel.
Yeah, the technology is pretty much there.
Yeah.
Without flogging that horse to death, at the end of the day, I still maintain that having something that is loaded by the pre-boot environment, which is always going to be slow, is not the right approach. You are just putting a kernel that has device drivers for the file system, for the block storage, for whatever it is you have, that are fast, that are optimized, and is perfectly capable of loading large files.
That's fine until someone encrypts your root file system with Chinese characters and they want to input it onto your graphical system before you have the root file system mounted. Yes, using a screen.
Well, but then you put it in your BIOS. I mean,
yeah. Like that's a long-standing problem that actually we wanted to fix, but we have never fixed. It's like it needs a lot of work in.
Oh, you have multiple routes, and you have an early route where you load from. And my point is, init RAMFS is not the right answer to this.
How is having a separate route different from having an init RAMFS? It still takes up disk space. It's still something
you wouldn't believe how much quicker the kernel is going to load that thing from, I don't know, U-boot.
Yeah, I think the problem is because Grub has to put it in from your disk, it's going to be faster than that. Because Grub sometimes can be quite slow doing that stage. For unknown reasons.
Only if you're running Grub still on BIOS boot, then sometimes the int13 stuff is slow. I've never seen disk access being slow in UEFI.
Yeah.
So, and you still need to maintain that separate root file system, and you need to keep everything on there in sync. So you're instead of having an initrd generator, you now need an initrd generator like Raycut and a separate special root file system generator, which you also need to maintain and yada yada.
And separate file system constraints because of additional partition.
So we know it's hard. Who's going to fix it? All right, I think we're finished with you.
The horse is dead.
I'll just someone online.
Oh, let me read. So Jeremy Linton says that EGK2 has an x86 emulator that can run x86 PCI option runs. This can bootstrap some AMD and NVIDIA cards.
Who would have thought?
Yeah, so when were you doing that in the PowerPC years ago, Ben?
Oh, yeah. But is this the 16-bit mode only one for old school BIOS ROMs, or is that a full protected mode one that can actually run EFI?
Yeah,
because EFI ROMs are a whole kettle of fish. They call through pointers. They have assumption on data structure, that having fixed offsets. Usually you can't do that. So it's probably just x86EMU for running the old school 16-bit ROMs and nothing else. Otherwise, insanity prevails. I mean, there's a reason why the bytecode stuff never flew with UEFI, right? It's just...
The answer here is that NVIDIA needs to provide an option ROM for the ARM systems so that they have their BIOS, so they have their screen before you get to U-boot, or, you know, like a real server would.
All right, cool. I've read that up there, yes. All right, well, thanks for coming, and hope you have a good dinner. Get out of here.